with, we will have Matt Bullimore, who will talk about unitary categorical symmetry. Thank you very much.
Okay. Thank you very much. Can you hear me well? Okay. So thanks to the organizers for the opportunity to speak. It's my first time here, actually, so it's a kind of great pleasure and really nice to present in this lecture theatre that I've watched lots of great talks in online. And so I'd like to talk about categorical symmetry and how it interplays with unitarity. So the talk is about symmetry broadly, and the type of symmetries that go beyond the paradigm of groups and representation theory and into the realm of things like higher categories and things like that. So there's been a lot of progress on these ideas in the last few years, and what I'd like to talk about is how those ideas interact with unitarity, and how unitarity is incorporated in those ideas. Okay. So I'll try to explain a bit more what exactly that means in a second, but let me just say that this is some work with my PhD student, Thomas Barch, and Andrea Grigoletto, who's a postdoc in Durham, and without both of whose kind of youthful expertise and enthusiasm, this project, I think, wouldn't have gone half as far as it has. Okay, so let me give a quick introduction to the ideas and what I'm hoping to achieve. So the talk is about symmetry in quantum field theory, and the general philosophy is that symmetries, we think about symmetries as topological defects in the quantum field theory. So there's some extended operators, perhaps, whose correlation functions don't depend too much on where you insert them, and so they have some topological nature to them. And so this type of picture, I think, was introduced in Sysmetry. Oops. Okay, that wasn't supposed to happen.
All right.
Let me just check. Okay, maybe I pressed the wrong button. Okay, so this type of idea, I think, was introduced or systematized in 2014, and there's been lots of progress since. And the kind of questions that I've been working on and trying to understand is what exactly is the type of mathematical structure that these symmetries have? How do we describe these topological defects in quantum field theory in an accurate way? How can we build interesting examples in higher dimensions? And not just that, how do you describe the symmetries? You know, perhaps they're not just groups, they're something different, but also how do they act on and organize the spectrum of observables in quantum field theory? So perhaps the analog of, if you have a group symmetry, this is like the analog of the Hilbert space transforming in representations of the group. How do they act on the quantum field theory? And the main thing that I want to talk about today is how unitarity, or it will really mean reflection positivity in my talk, is incorporated in this set of ideas. And so again, with this analogy, this is kind of like, well, in quantum mechanics, symmetries act by unitary operators on your Hilbert space. And so this is supposed to be the kind of analog of that idea. Okay. So what's the plan? So the plan is that I'd like to begin in the first half, really, just by looking at some low-dimensional examples, just to kind of give an idea of what's going on, the type of examples we're interested in, and what they can tell you about the general case. Then I'll try to say in part two a bit about the kind of general expectations that we have for the type of mathematical structures we're talking about. And I'm trying to be a bit cautious with the language here because this is really going to be expectations, because I think that the math has not quite been developed yet or is in development. And then I want to give a large and interesting class of examples called solitonic symmetries, sometimes called topological symmetries, where these really have a concrete realization. And then at the end, I'll give some further applications. Okay, so let me crack on with some basic examples. So I want to start at the beginning with quantum mechanics and just review some very basic things. So I want to think about a quantum mechanical system in one dimension and imagine that it just has a finite group symmetry. And so one thing we know is that in this case that there are some unitary operators that are labeled by elements of the group. They commute with the Hamiltonian. That's what we mean by symmetry, and that they're unitary. And the fact that I have a group symmetry is captured in how those operators can. Okay. Maybe it's because I'm holding it rather than clicking it. Is that the issue? Okay. Okay, that's all it takes. I can.
Control L.
Yeah, okay. Yeah, so the fact that it's a finite group symmetry is just encoded in how these guys compose. So namely, if I take two, well, they compose according to the group law, perhaps up to a small projective phase, alpha. Okay, I can see that I'm going to need to click a bit faster. Okay. And that small projective phase, it's exactly the one that Aaron was talking about yesterday, at the end of yesterday. What happens is you don't quite get a representation of your group on the Hilbert space, but you get a projective representation. And this is capturing the idea of an 't Hooft anomaly. So in this case, just in one dimension, there's a two co-cycle alpha. It's just a small phase that captures the anomaly. And then the Hilbert space can transform in a projective unitary representation of the group. Okay. So let me now reformulate this statement slightly in the language and how we like to think about categorical symmetries, which is namely we think about them as topological defects. So in this case, we're just in one dimension. We're living on a line. And the topological defects are just local operators, points. And they're going to be oriented points. And so now we just have some topological defects. They're points. And they're labeled by group elements. And they commute with the Hamiltonian, so you can move them up and down the line as you will. And what do you get? Well, if you study these local operators, you find that they generated an algebra, which is the twisted group algebra, by taking linear combinations of these generators and looking at how they compose. So for example, I can take two group elements here, and I can compose them. And then I reproduce the group law up to a phase. But there's also a bit more structure. The extra structure is that it has a C-star algebra structure. So this basically means that there's a notion of dagger or star or an involution on the algebra. And this acts in the following way. So it basically takes a group element and it sends it to its inverse, up to a phase, perhaps. And one thing to notice is that this star here, this involution, the way it acts is essentially very similar to reversing the orientation of the point. So if I reverse the orientation of the point, I get the opposite group element, or the inverse group element. And so conjugation is essentially the same as orientation reversal, perhaps up to a phase. And so another name for this algebra, or this type of a finite dimensional C-star algebra, I'm going to call this an O1 dagger algebra. And this is supposed to capture the idea that the dagger structure, or the star, is very closely related to reflections in this case, which is O1. And so this is a notation that I'm borrowing or adapting from this paper here. Control L, you see. Thank you. Thanks. Sorry. Okay. So yeah, I'm going to call this a finite dimensional O1 dagger algebra. And the reason for doing this is that this notation here is going to generalize to the other things that I would like to say. Okay. Okay, so this is basically one dimension. It's just a reformulation of symmetries in quantum mechanics in a language that is hopefully going to allow me to lift this to higher dimensions. So let me go on to 2D now, so to a two-dimensional system. I'll be thinking of it in a Euclidean picture. But again, the idea is the same. I just want to look at a system with a finite group symmetry, so finite group G. And what this means now is that instead of point-like defects, I've got some topological line defects now. And again, those line defects are labeled by group elements. they have an orientation, and if you flip the orientation of the lines, then you take the inverse of the group element. And now the lines can compose in this type of manner, which again captures the group law. So the group law is in composition. But now the defects are topological, but you have to be a bit careful. There can be additional extra phases as you look at kind of isotopies of the graphs. And in this case, you get exactly such a phase when you look at the associator, or this type of picture here, where you compose 3 group elements in different orders. Depending on which orders you compose them, you might get an extra phase. And in this case, the phase is captured not by a 2 co-cycle, but by a 3 co-cycle. And again, that's interpreted as a 't Hooft anomaly for this symmetry G. So let me now just try to relate that back to perhaps a more familiar picture of symmetries in terms of operators acting on a Hilbert space. So to do this, let's just think about for a second the Hilbert space on a circle. Okay, so we're quantizing the theory on a circle. And I apologize that my kind of time direction is going along the horizontally. It's going to help me to draw the pictures a bit more easily. And so what type of structure do we get by putting the theory on a circle? Well, now I can wrap the line defects around the circle, and they will act as operators on the Hilbert space. And you have a very similar structure, so namely the operators can compose according to the group law. And again, there's a notion of dagger structure or conjugation, which takes a group element to its inverse again. And so this generates a group algebra in exactly the same way as before. But in this case, this doesn't really detect the anomaly in this case. Okay, in one dimension, the anomaly was a 2 co-cycle, and I could see this in the structure of this composition. But now in 3 dimensions, we have lines. The anomaly is a 3 co-cycle, and so I'm not going to see it in pictures like this, unfortunately. So you might ask yourself, well, what do I need to do to see the anomaly? And one thing you can do to detect the anomaly is to not just look at the Hilbert space, but to look at what's called the twisted sector Hilbert space, or to add in twisted sectors for the symmetry. Okay, so what does that look like? Well, it looks something like this. So you can now imagine that you have twisted sectors. So what does that mean? It means that you've now inserted one of these line defects, in this case horizontally. So this is what I'm calling X. So the twisted sector is labeled by X in this diagram. And so there'll be a sector in the Hilbert space, a summand for each of these X's. And then you can ask yourself, how does the symmetry act on this structure, on the full Hilbert space, including all of the twisted sectors? And something interesting happens because of the way these lines compose, then the twisted sectors can get mixed up. They get transformed into each other by the group elements. So I think I didn't quite draw it on the picture, but the idea is if you have a twisted sector labeled by a group element X, if you act with a group element G, then it will act by conjugation on the twisted sector. So this now sees the anomaly. The reason is because you're getting intersections now between line defects. But nevertheless, you still generate a very nice algebra structure. So in particular, you can start composing these intersections. And again, you find that they compose according to the group law up to some small phase. And that phase is going to detect the anomaly. And again, there's a notion of dagger structure. So you get a C-star algebra. And again, it's with respect to the group element that's acting, it acts by taking it to its inverse up to some phase. And it kind of flips the direction of the diagram. So it takes something that's acting to the right and produces something that's acting to the left. So what structure does this have? Well, it generates what's called the twisted Drinfeld double, or the twisted groupoid algebra for the action of G on itself by conjugation. And the twist here refers to this phase tau. And in terms of the anomaly, there's some expression here, but it's what's called the transgression of the 't Hooft anomaly. So it's some combination of these phases that appears in this factor. And it appears both in how these defects compose and also in the star structure here. Okay. So again, this is an algebra. It has a product. It has a star. They have some nice properties, and it has this structure of a C-star algebra, or an O1 Dagger algebra. Okay. So this is pretty much it for group-like symmetries. Question?
Is this map from alpha to tau always invertible?
Yeah, it's a question I should know the answer to. I suspect probably not, but...
Because that would mean that there are anomalies that you cannot capture this way.
Yeah. It's a good question. I don't think I know the answer. But yeah, I would agree with you that if that's the case, there would be anomalies that can't be captured. Yeah. I should say, I mean, even worse is true, in some sense, that you can have different groups, I think, that have the same group algebra over the complex numbers. So something even worse than that is true. Okay, good. So this is all I want to say about invertible symmetries. So let me now give an example of a non-invertible symmetry. And so one thing perhaps to say here is that, you see, I didn't really need to do this. I could have a kind of well-defined subsector, a well-defined subalgebra by just throwing away the twisted sectors. But it's kind of useful to introduce them. I see the anomaly. But when we come to non-invertible symmetries, the difference is that I really need the twisted sectors to get a reasonable structure. Let me give an example, which is a small variation on what we just did. So I'll call this for now a Tambari-Yamagami symmetry. So it's basically what we had before, except I'm going to take the group G, I'm going to call it A, and require it to be an abelian group, and I'm going to require it to be anomaly-free. And then we're going to supplement that structure by just one additional line, which is non-invertible. Okay? That I'll call N. And N has the property that it's self-dual, and also that if you take its fusion, it can fuse into any of the other group elements A. Okay, so it has a fusion rule that looks something like this here. The N squared is a sum over all of the other group elements, and because of that, this is not really an invertible. It's a non-invertible symmetry. Okay, so it has some behavior like this, and then there's some additional data that you need to give, not just the line, but you also need to give some more data that fixes all of the associators of N with itself and with all of the other group elements. And that gives some additional data. And you have to choose a kind of bicharacter, chi, and then there's a choice of square root. Okay. So this type of structure was introduced in '98 by Tambari-Yamagami. And various examples of this can be realized in various physical systems. For example, the Ising symmetry comes from taking this group just to be Z2 and appears in the critical Ising model. Okay, but other than that, we want to play the same game. We'd like to understand, so suppose now that I put my system on a circle, and I ask, well, how does this symmetry act on the Hilbert space? And in what sense is that a unitary action? In what sense is it compatible with quantum mechanics? But the idea is very much the same. We need to look at not just the Hilbert space on a circle, but the Hilbert space with all the twisted sectors. So there'll be a twisted sector labeled by each of these lines. And then all of the elements can now act on the Hilbert space. And they generate, again, a type of algebra that you get by doing this. So here's, I didn't want to write it all out, but here's one example. So in the example here, I'm just looking at the twisted sectors labeled by A, that are labeled by the group elements A, the invertible elements. And then I'm looking at how the new duality defect, or non-invertible symmetry N, acts on those. And again, it can act by, it can interchange all of the twisted sectors. It can change one twisted sector to another. And it does so with various phases that are captured by these, well, this additional data that we had to specify. Okay. So in particular here, if I act twice with N, I can get any group element in the middle, and I have to take a sum. And sorry, that's for a fixed group element B in the middle, I get a sum over invertible elements C that are acting, and then there's some extra phases that captures this data. And again, you can equip this with a star structure or a dagger structure quite naturally, and it acts in the following way. Again, N is self-dual, so this structure is perhaps not unexpected. And if it acts by taking twisted sector A to twisted sector B, its dagger will do the reverse, up to a small phase. So this type of algebra that you get by putting the theory on a circle is sometimes called the tube algebra of the symmetry. And again, in this instance, it has the structure of a finite dimensional C-star algebra, or O1 dagger algebra. And again, you can go away and classify all of the irreducible representations, unitary irreducible representations. There's a finite number of them. And so your Hilbert space will then decompose into these irreducible representations. And the idea is that that captures the implications of your symmetry as far as your quantum system goes. Okay. So these are some examples. So what type of structure do we need in general in 2 dimensions? Well, this is already fairly well known. And what I didn't really say in the previous slides is that the structure that I was starting from that governed my topological line defects was that of a unitary fusion category. So let me try to give a brief overview of the structure that has intuitively. So the first thing it has is duals of objects. We saw examples of that in the previous slides. This is the thing that I get by flipping the orientation of the lines. So in the group-like case, it was taking a group element to its inverse. The thing that I didn't show quite explicitly was that you need a dagger structure on morphisms. And then you need some kind of compatibility between these things that tells you how they interact. And the basic idea of that is that whatever that structure is, it should ensure that you can have a almost consistent graphical calculus, so where you can draw these line defects and insert them as you like on oriented 2 manifolds.
Autofunctor?
Yeah, I think that's
So yeah, what is that? So that's an autofunctor on this fusion category?
You can lift it to such a thing, yeah.
And okay, so it acts on both objects and morphisms, and on objects it's the usual duality.
No, the dagger is going to act trivially on the objects, so.
Okay, so it acts trivially on the objects, and then it's if you had a linear category, it would. Oh, sorry, if you had a linear category with a Hermitian structure on the morphism spaces, then it would be ordinary adjoint.
Yeah.
Okay.
Exactly. Yeah. Just so. Okay. So again, this is a unitary fusion category. All of the examples I gave have this structure. And borrowing or adapting the notation from this paper, I'm going to call this an O2 fusion category, or O2 dagger fusion category. And again, the idea, it's O2 because I'm in 2 dimensions now. I'm working with oriented theories, but there's a notion in which the dagger is very closely related to reflection, and so that's what this O2 dagger notation is supposed to be capturing. Okay, and so what's the general idea? Well, the general idea is that given a unitary fusion category, or an O2 dagger fusion category, there's a notion of integration. Or let's say it the following way. So the way that fusion category is going to act on the Hilbert space, more generally on observables in quantum field theory, is by performing a kind of integration of that category. So this is some version of factorization homology, I think. But I'm just going to use it as a notation here for now. And so the idea is really being that you're putting the theory on a circle, you're kind of integrating your structure in some way over that circle to produce an algebra that actually acts on the Hilbert space. That's the intuition. So at the moment, this is just some notation for this slightly vague construction that I've given in examples, where from some fusion category you can produce a nice algebra, or a nice C-star algebra. But the basic point of this is that if you ask yourself the question, well, what structure do I need to put on my original category in order to get a nice C-star algebra that's compatible with quantum mechanics, then the answer is it needs to be a unitary fusion category. And you need all of that data on the previous slide to reproduce this nice C-star structure. Or to say it more formally, if you start with an O2 dagger fusion structure on your original symmetry category, that will ensure that you have an O1 dagger algebra structure on this tube algebra, the thing that acts on the Hilbert space on a circle. So the idea is that this is supposed to provide some kind of link or direct link between perhaps two different notions of unitarity. On the one hand, there's a kind of math notion. You have a unitary fusion category. And on the other hand, you have a more perhaps standard physics notion in terms of a Hilbert space in your quantum mechanics. And this is supposed to provide a direct link between those two pictures.
This integration, the endomorphism, identity object. So, I mean, there's another way you can go from, you can reduce category number,
Yeah.
I'm sure you know, which is looping. So if you have a monoidal n category, you can go to n minus 1 by taking the endomorphisms of the identity object. Is that what this integration is?
No, it's not quite that, but it's very close. It's a bit more like taking a sum of simple objects and then taking endomorphisms of something like that. So it's close to that, but not quite that. Okay, so this was 2 dimensions. What about higher? So when we go up to 3 dimensions, already things get quite a bit more complicated for a number of reasons. So on the one hand, you can have lines and surfaces now. You can also study the Hilbert space. There's a lot more choices, right? You can pick some closed surface, a 2-sphere or torus or so on. And there are going to be lots of different types of twisted sectors that you can consider. So I'm not going to try to give the full structure, but just try to give a kind of example, basically. So here's my example. It's very close to a finite group. It's what's called a finite 2 group. The simplest type, a split 2 group. There should be some references here. I apologize for that. But what's the basic picture? The picture is that there are some surfaces that are labeled by group elements G, of the group G. There are some line defects, some topological lines that are labeled by elements of the one-form symmetry group A, that's abelian. And there's an action of one on the other, which is interpreted in this way, is that if you have a line that pierces the surface, it comes out the other side with the action. And again, there's a notion of a 't Hooft anomaly. Well, there are lots of 't Hooft anomalies in principle, but I'm going to look at a particular one that's labeled by a 2 cocycle on G with values in the dual of A. And that's captured in a very similar way to the previous slides. You study the composition of pairs of these surfaces with a line going through the middle. And they don't quite compose according to the group law, but they do so up to some small phase that's constructed from the anomaly. And so again, you can ask yourself, well, suppose that I now put this on a sphere or a torus. What structure, what algebra do I get, and how does it act on the Hilbert space? So here's the picture. So let me just focus on the simplest case, which is a two-sphere. Then it's almost identical to the previous slide. So in particular, you have the group elements compose in this way, just like in the previous slide, and there's a natural notion of a dagger structure. And it generates a very similar thing, a kind of twisted groupoid algebra in this case. But again, the main point is that there's a very natural way to integrate over a two-sphere to produce an algebra, a C-star algebra, and then that acts on the Hilbert space. Okay. So what kind of general structure? Well, again, we're kind of lifting up one dimension. And the idea is that the thing that we need to start with is now a unitary fusion 2 category. So there's surfaces and lines and points. So there's one level higher. And it comes equipped with a whole load of structure. There's a notion of duals on objects. There has to be now 2 notions of dagger for 1 morphisms and 2 morphisms, and a whole bunch of compatibility conditions between those 2 things, whose idea is to ensure that you can consistently or almost consistently draw these types of pictures that I've been drawing. Okay. I write that because of a 't Hooft anomaly is in some sense a slight obstruction to having a perfect graphical calculus, I would say. That's all I mean by that. Okay. And again, just like before, I mean, it's exactly the same, but the idea is you want to start with some structure, in this case, a unitary fusion 2 category. There's some notion of integration over a surface, and you can produce from that a C-star algebra that captures how this acts on your Hilbert space. So this should give some motivation for the kind of structures that we'd like to put on symmetries, on these type of higher fusion categories. And so in the second half of the talk, I want to talk about what the kind of general expectations are for those structures more broadly. Okay, and so here, well, before I do that, I want to say a few words about symmetry type. And so Aaron did me a favor yesterday in describing this really nicely. So really, before you start, you should ask yourself what type of fields you have in your quantum field theory. Does it have just bosons? Does it also have fermions? Does it have time reversal symmetry? And so on and so forth. And attached to that type of data, there's a notion of symmetry type, which captures these things, which is a choice of tangential structure. Okay, and this structure, in some sense, it encodes these principles of relativity and unitarity. So relativity is captured by the fact that this tangential structure should be relativistic, which means in some sense that the symmetries should contain SON. I'm in Euclidean signature here. And then unitarity is encoded in what's called the extended symmetry group. So it's a Z2 extension of this H. And that's capturing this extra kind of reflection that you need to add that must be correlated with the daggers. So this type of structure was described nicely in the work of Fried and Hopkins, reflection positive field theories. And so everything that I've been saying so far in my examples have all been this line here. So I've been looking at oriented theories, say with just bosons. In this case, that extend, so H there is SO. The extended group is O. That's why I've been writing O dagger everywhere. But in principle, one needs to, you can have all of these structures for all of these other choices as well, and you should be able to formulate these structures in those cases too. So what type of structure do we need? So the idea is that symmetries, or more particularly finite type of symmetries, are captured by a collection of categories. So I'm going to label them by two indices here, n and d. So d is always going to be the Euclidean space-time dimension, and n is going to be the dimension of the topological defects that I'm looking at. So that means that n is also the categorical degree. It's an n category. And its structure depends very much on this choice of tangential structure, or the symmetry type. And then there's some relation between all of these objects that captures the idea that, well, if you have an n-dimensional defect, one way to view that in a silly way is it's a junction between trivial n+1 dimensional defects. And there's some structure that goes along with that I think I won't describe in any more detail. So the question is, well, what structure exactly do these higher categories have? And that, of course, depends on this choice of tangential structure. And I want to kind of give some hopes or words, or maybe a bit more than that, but expectations about the structure that these categories have. And the reason I say expectations is because largely I think the mathematics is still under development. So the idea is that you pick a symmetry type. So in all my examples, it was SO. And then this category CND that captures the n-dimensional defects in d dimensions is what I'm going to call a H hat D dagger E D minus n fusion n category. So there's a lot going on here. Okay, so let me try to unpack it a bit. So first there's the n category. This is the idea that the defects are n-dimensional. Okay, that's what that's capturing. Then there's the fusion structure, and that's telling you how the defects confuse. And so that cares about the codimension of the defects. It tells you what the transverse space looks like when I'm trying to compose them. And then there's the really important thing for this talk, which is this H dagger structure. And that's the thing that's really capturing unitarity or extended unitarity. And the basic idea is similar to the examples, but there's a whole bunch of structures here, including duals and daggers for all the various morphisms, and they have to obey some compatibility conditions, with the idea being that you can consistently draw the type of pictures that I've been trying to draw in a consistent way. And I think that there's hope that we can make the structure very precise using some very recent work on dagger n categories. Okay, let me give a couple of examples. I'll just go back to the examples that I've already done to tell you what they look like. So if I take the symmetry type to be SO...
Sorry, Matt, could I ask another question? I'm really confused about what you're doing here. So
yeah.
In the cobordism hypothesis, we have, to an n-dimensional field theory, we would associate an n category, right?
Yeah.
But you have many n categories. Are you just de-looping them?
No. No.
Why do you, in the cobordism hypothesis, you would have, for an n-dimensional field theory, you would have a single n category, and that captures all the structure of the defects. So why do you have separate n categories?
This is more like the tangle hypothesis. Okay, so what I'm doing is I'm looking at n-dimensional defects in d dimensions. Okay? And so when you look at the tangle hypothesis, there's not just one category, there's a whole set of them. So this is very much analogous to that. They're not all unrelated because of this type of relation here. So they're not necessarily de-loopings of each other, but they loop down to the, yeah.
So what's the arrow? Is that a morphism or
that's
an equivalence or
that's
what?
an equivalence of whatever structure that I'm
Okay.
describing on the next page, yeah. So if you like, you could take the top one, and that would be enough, but okay, so here's some examples. So an O1 dagger E1 algebra, that's just the thing we started with. That's a finite dimensional C-star algebra. There's an O2 dagger E1 fusion category. That's a unitary fusion category. This again describes symmetries in 2D and similarly in 3D. And then you can look at other symmetry types, and so spin is giving you something like super versions of these or Z2 graded versions of these. And then if you want to look at theories with time reversal, then you're kind of supplementing these things with a type of reality structure that interplays with this in a certain way. Okay. And then the general kind of idea is that the action of symmetries on a quantum field theory on kind of observables, like the Hilbert space or perhaps something else, comes from taking this structure and integrating it over some space. So one example, so for one thing to have in mind is if you're interested in, say, operators of a given dimension, you should take the sphere that links them, and that's the thing that you want to integrate over. So an example that we've already done is when you take the symmetry type to be SO, you take n and k both to be d minus 1, so I'm looking at codimension 1 defects. And then if you integrate this symmetry category over a codimension 1 manifold, then you're just going to get an algebra, C star algebra, and that's the thing that will act on the Hilbert space unitarily. Okay. So in the last 10 minutes, I want to talk about a particular class of examples that I'll call solitonic symmetries or topological symmetries. But I really want to go back to an even simpler case, which is no symmetry at all, because this is already slightly non-trivial in this setting. So before I get to solitonic symmetries, let me say something about the case where you pick a symmetry type, so SO or spin, but you have no internal or global symmetry. So this is the most trivial case. But you still have something non-trivial in this structure because you can always take some TQFT that can be embedded in higher dimensions, and you can just plonk it on some manifold inside of your space-time, and that will give you some topological defect. It's a very trivial one, but it's there. So another way to think about this is that whatever this structure is, it's a bit like the coefficient system that you're working with. You can always stack your topological defects with kind of decoupled trivial ones. And so we should understand this first. And so the basic mantra here is that n-dimensional defects are basically n-dimensional TQFTs that you can embed in d dimensions. And this is the type of thing, this is the realm of the Tangle hypothesis. I won't say too much about that, but just to say that these categories are really variations on finite dimensional higher Hilbert spaces, or n Hilbert spaces, or a slight refinement of that idea. So let me try to give a few examples just to set the stage. And again, let me focus on the SO, the oriented case, in which all... So first of all, for point defects, we're just looking at, topological operators. There's not much going on there. There's not much that can happen. And it doesn't matter, what the dimension that you embed the points in. There's basically only a single point operator, the identity operator, that you can multiply by complex numbers. And so in this case, all of these things are basically just C. But this notation is supposed to capture what structure you're equipping C with when you do these computations. And that's slightly different. So in the zero case, this is just points in 0 dimensions. It's basically just C as a vector space. If you go up to 1 dimension, points can compose and form an algebra. That's just C as an algebra. And if I go to higher dimensions, well, the points can now compose in higher dimensions, so it has to be commutative, which of course it is, but this notation is capturing what structure it could a priori have. Okay, and then we go up to line defects, and we recover things that are fairly familiar. So if you have just line defects in 1 dimension, Well, that's just a category, in this case a unitary category. If you have lines in 2 dimensions, that was a case we studied, that we looked at earlier, you're in the business of having a unitary fusion category. Lines in 3 dimensions can braid, so you get a braided fusion category. And then higher up, everything stabilizes, and you get a symmetric fusion category in this case. And in this case, they're all just variations on the category of Hilbert spaces and linear maps, or finite dimensional Hilbert spaces and linear maps, where the dagger structure is exactly dagger on adjointive linear maps. So this type of structure really forms the kind of coefficient system, or the base that you have in the game. And so, well, what about surfaces? If I go 1 dimension higher, this is where things become a little bit more intricate. It's a bit harder to say exactly what a 2 Hilbert space is. And in particular, there's a difference between what I call Hilb 2-2 and what I call Hilb 2-3. And that's very closely related to ideas to the existence of Euler TQFTs, which are TQFTs that are kind of fine inherently as a TQFT, but can't necessarily be embedded in a higher dimensional space-time. And so you have to distinguish these types of things. Okay. So let me then come in the last 5 minutes to say a few words about solitonic symmetries. So what's the idea? Well, the idea is that these are the symmetries that you get in a sigma model. And they're the type of symmetries that come from the topology of the sigma model. So an example would be a winding number symmetry. The reason we say they're solitonic symmetries is because the type of charged objects or charged operators you get are topological solitons, or behave like topological solitons. So the idea here is very similar to that before, but now you think about the n-dimensional defects as not just n-dimensional TQFTs that can be embedded in d dimensions, but you have to equip those TQFTs with a coupling, in some sense, to the space X or to the sigma model. So that gives a bit of extra structure to these things. And the way that can be encoded is that you essentially study some version of higher local systems on the target space X. So what does that mean? Well, these are symmetries that know about the topology of the target. And in fact, if I'm asking about n-dimensional defects, all they really know about the target is the homotopy n-type, which you can think about as being captured by this homotopy n-groupoid. And then you look at functors from that, preserving the appropriate structure into these universal categories or coefficient system. So this is a kind of variation on the theme of representations of the fundamental group or local systems. It reproduces the known invertible symmetry, and it gives you a large class of examples to play with. I think, given that I'm out of time, well, let me just give one example, which is a sigma model in 4 dimensions to CP1. This goes slightly outside my assumptions, but I think is still valid in this instance. And in this case, you can really kind of classify the type of symmetries you get by studying these functors. And the type of symmetry that you get has appeared in this type of Q mod Z type classification that you find in a whole bunch of interesting examples, like the CP1 sigma model in 4D, but also electrodynamics and other things. Okay, I think given the time, I ought to finish there. There's a few applications, so I'll maybe just leave those. Thanks a lot.
Thanks, Matt, for the great talk. Time for questions.
Thanks for the talk. So I guess for fusion categories, we can check whether it's unitary by checking whether the corner dimensions are positive and making sure the associators are some unitary matrices.
Yeah.
So for fusion 2 categories, do we have a statement in terms of the 10J symbols? Or?
I don't think we're at that level yet
Okay.
of development, yeah. I don't think the technology exists yet to answer that question,
Okay, thank you.
as far as I'm aware.
Hi, could you more precisely situate what is happening in this talk with regards to the cuboidism hypothesis? And are you telling us something old, something new, an old thing in new ways, or what exactly is the relationship?
Yeah. Let me try to say a few more words. Maybe if I go back to somewhere along here. So what I'm trying to do is a unitary version of the Tangle hypothesis, okay, of which I think you can view the cuboidism hypothesis as a certain limit. So in that sense, it's like I'm trying to do a kind of unitary version of the cuboidism hypothesis. Okay, so this collection here, I mean, if you take kind of n to be, well, okay. I think to recover the situation of the cuboidism hypothesis, what you're really doing is trying to take d to be very large. So,
I'm with Tangle hypothesis instead.
You happy with that? Okay.
Yeah. How is it different from Tangle hypothesis?
Then I'm basically trying to do, so the Tangle hypothesis, or a unitary version of the Tangle hypothesis, is basically supposed to be the construction of this universal example of higher Hilbert spaces. Okay. And then I'm trying to kind of abstract the structure that those categories have a little bit away from the Tangle hypothesis and ask and propose that symmetries more generally should have that structure. You know, symmetries are about, you know, topological defects in a fixed space-time dimension. So this is...
So you're saying beyond topological QFTs?
That's certainly true, but that's not the sense in which I meant.
So what does abstract mean? What's more abstract than Tangle hypothesis?
Well, this is only one example. This is Hilb, okay? But there are many other type of examples. So, well, okay. The example I talked about here with solitonic symmetries, that's also could be viewed as an example of the Tangle hypothesis, where you're equipping the tangles with extra structure of a map into some space X. So again, that could also be viewed in the realm of the Tangle hypothesis. But I don't know if all symmetries are like that.
Further questions?
Hi, Matt. Thanks for the talk. Well, usually one feature of symmetries that we highlight is that symmetry tend to act on things. There is a and this action, if we want to say that a symmetry is a symmetry of a quantum field theory, has to be faithful. So there should be some notion in which the symmetry acts non-trivially on some operators, maybe some local operators or extended defects. Or can you comment on that, or is there a...
Yeah, so I mean, I guess that's a question of completeness in some sense, right? So, I mean, maybe if I take you back all the way to my very first, let's go back to Tambari Yamagami, for example, right? You might expect, you know, in this case, just in 2 dimensions, you can really classify the number of irreducible representations, and, right? And if you have the symmetry, you would expect to see all of them appear. Right. So to give an example, if you take the critical Ising model, there are, how many are there? There are 9 irreducible representations, and I think all of them are realized once in terms of chiral primaries. So it has all of the structure there in a minimal way. So, and the general idea would be similar to that, right? Is that once you're able to classify this structure, classify the irreducible representations, or perhaps higher representations in this case, then you should expect similar comments there. That's the idea.
Maybe just to follow up about tangle hypothesis. I would have thought that unitarity would be about, maybe you even said this, about time reversal or something like that. So I would have thought to get a unitary version of tangle hypothesis, you would just say something like, take tangle hypothesis, take fixed points, like maybe homotopy fixed points under some involution that comes from imposing time reversal, and then there's your answer. So how is that related to...
I very much hope that you can derive what I'm writing here in the manner that you just explained. That's beyond me at the moment. But I completely agree with that philosophy, yeah.
Further questions?
Is there a clear notion of non-invertibility for the topological point-like operators?
But could you say the word again?
Yeah, I'm sorry. So is there a clear notion for non-invertible symmetry for topological point-like operators?
Yeah.
I mean, for extended operator, we can define simple objects, and then starting from that, we define fusion rules, and then we know it's non-invertible, right? But
Yeah.
for point operators,
Yeah,
is there a
that's
clear
right.
notion?
Yeah, so this maybe goes back to an earlier question in some sense as well, but yeah, so basically, the structure you have here is a finite dimensional C-star algebra. So these are pretty simple. They're just all they're always a sum of matrix algebras, finite dimensional matrix algebras, where the star structure is given by adjoint on each of the factors. So the question is, can you realize all of those as the group algebra for some finite group or perhaps twisted group algebra for some finite group? I think the answer is yes, but...
Yeah, because at the practical level, I can just make my favorite complex coefficient linear combination of any point operator to make a new point operator. So it seems like whatever fusion rule I write down, I can always rewrite it in terms of some finite group
I think so,
symmetry.
yeah. And as I said earlier, there's the feature that, I think if you take D8 and Q8, I think they have the same group algebra over the complex numbers, for example, so, yeah. Whereas if you change the symmetry type, for example, if you were to do O rather than SO, you would be over the reals, and then you would detect the difference.
Okay. Well, if there are no further questions, let's thank Matt again for the great talk.
Bobby? Closer. Maybe it's, actually, if you take this out, because if it goes on the microphone, it makes noise.
Just put it.
Yes, in the pocket or whatever you want.
So for the pointer, can I just direct?
Yes, you can point wherever you want.
Okay, I see.
There, it worked. There is an accelerometer. There is, so you can point
I see. Yeah.
wherever you want. If you keep press it,
Okay.
it goes out of full screen.
should not.
So try not to keep this
Okay.
pressed.
Yeah.
So
Okay.
just press it. Otherwise, Control L, I can help you, but Control L goes full screen.
Good. Thank you.
You have 50 minutes. I will be showing you.
Ah. Okay. Yeah. I will control the time. Yeah. Should be fine.
Very well. We can start again. Next speaker is Yalong Cao, who will talk about towards the complexification of Donaldson with TQFT. Thank you very much.
Thank you very much for the introduction and this invitation. So I will present a joint work with Gufang Zhao from Melbourne and Zijun Zhou from Shanghai. So let me first record this four manifold Donaldson theories. So we start with this. Sorry. Okay. We start with this real-oriented four manifolds, closed, and we can consider Donaldson invariants which counts so-called instantons or anti-self-dual connections on these four manifolds. And we can consider this, the four manifolds decomposed into this union of two four manifolds with boundary along this D, and consider the gluing formula which relate to the relative invariance here and the Donaldson invariance on the closed four manifolds, which fits into this Donaldson-Witten TQFT structures. So now we are interested in the complexification of this left column. So we consider this complexification of real-oriented four manifolds, which is a complex fourfolds with a holomorphic volume form. So we are considering Calabi-Yau fourfolds. And the analogy of Donaldson invariance in this case is so-called Donaldson-Thomas invariance, which counts a similar instantons, but it's so-called SU4 instanton because this is a Calabi-Yau fourfolds. And because now we are in the algebraic geometry setting, so there are much more things we can do. We can actually count coherent sheaves, algebraic geometry objects on this Calabi-Yau fourfolds. So similarly, we can consider degeneration of Calabi-Yau fourfolds into the union of two fourfolds with along common anti-canonical divisor D. So D is now an anti-canonical divisor of both y plus and y minus. So by adjunction, we know that D itself is a Calabi-Yau threefold. So the question we want to discuss today is what is the analogy of gluing formula here, and also potentially what is the underlying TQFT in this sense. So because there's a TQFT structures, so let me first talk about this vector space associated to this 3D theory. So in the real case, we start with oriented closed real free manifolds, this D. And there's a Chern-Simons function on this space of all connections. And we can consider the so-called instanton Floer homology. Roughly speaking, this is the infinite dimensional Morse homology of this Chern-Simons functional. So in the complexification case, we consider Calabi-Yau threefolds. So we know that there's a holomorphic Chern-Simons. And there's a holomorphic cousin of this instanton Floer homology, which roughly speaking is the infinite dimensional version of this vanishing cycle shift homology associated to this complex value functions. But this is an infinite dimensional case. So to make sense, this right-hand side, we just need to be precise. So MD, let's say this is a moduli of bundles or sheaves on our Calabi-Yau threefold D. To make sense this homology theory, so the key structures, the following theorems due to Pantic-Thorne, Vakier-Vezzosi, and Brass-Boozy joints. So which roughly says this moduli of sheaf on Calabi free for D has a derived enhancement with -1 shifted symplectic structures. And the key property of this -1 shifted symplectic structure locally is it can be written as a critical locus of functions on this smooth variety U. So now the idea is that we want to glue this local perverse sheaf for vanishing cycles along this on this global moduli space, and we want to take the hypercohomology of this perverse sheaf. So this gluing is done by these two groups of people, and in the gluing we need the so-called orientation data due to Conservatory and Soberman, which is a square root of the virtual canonical bundle. But let's say for simplicity today that MD is a global critical locus written as from a smooth variety W and a regular function or polynomial function on this smooth space W. And MD is this global critical locus. So we don't need to worry about this gluing in this talk. So in this case, our state space, just HMD, is the vanishing cycle homology. Also, people call it as a critical homology because it's relevant to the critical locus. And in some situation, we also add the equivalency with respect to this flavor symmetry F0. So let me give you two examples of this critical locus. The first is relevant to the so-called gauge linear Sim model. So we consider this W to be the total space of this canonical bundle of P4, and we present as this C star quotient. And we can write this function phi to be this P, which is the coordinate of C, times this polynomial, x1 fifth power to the x5 fifth power. This x1 to x5 is the coordinates on C5 here. So then we can take the critical locus of these functions and check that this is the hypersurface in CP4 cut out by this polynomial equations, which is the famous quantity-fruitful. And then in this case, the vanishing cycle sheaf homology reduced to this Borel homology of this quantity-fruitfuls. So we recovered this quantity-fruitful homology. So this is a compact example where there's a critical locus is a compact manifold. And let me give another example, which is non-compact. So it's given by so-called quiver with potentials. So here we draw this diagram of this quiver. We have this circle vertex, we have this box vertex. We consider this certain maps between these vertexes. And here we have three loops and this one framing path. And let's consider the representation of this quiver where we give this vector space V in this circle vertex, and we put a one-dimensional vector space in this framing vertex. And then the representation space is basically considering this home from V to V, because this is a loop. And we consider this 3 times of this home space because we have 3 loops, ABC. And we consider this home from C to V, which I just write V here. So this a gauge group, GLV, acts on this representation space by just conjugation action here, and also a left or right multiplication, depends on the notations. And this function now is written as a trace of this A times B bracket C, where this B bracket C is this standard bracket in the matrix. So in this case, there's an interesting flavor symmetry. F, which is a C star free. I just write this action here. This is coordinates T1 to T free. It's the coordinate for C star free. And the X on ABC just by standard just left multiplications. And we take a subtorus, which preserves this holomorphic volume forms. So it's T1 times T2 times T3 equals to 1. So this is a 2-dimensional torus. So in this case, the critical locus of phi is the so-called Hilbert scheme of endpoints on C3. And this is non-compact because C3 is non-compact. And the interesting thing is that it's equivalently compact with respect to this flavor symmetry F0. And the fixed point is labeled by this so-called 3D Young diagrams, where we relate 3D boxes. And the number of boxes is this given n here. This is the dimension of the vector space. And in this case, the Venetian cycle shift homology, which I take to be equivalent Venetian cycle shift homology with respect to this favor symmetry group, is the so-called fits into this cohomological DT theories, which is relevant to the subject of geometric representation theory. Okay, so now let's talk about this relative 4D theories, where this our fourfolds come in. And we start with this YD is a smooth log Calabi-Yau 4 pair, where this Y is a smooth fourfolds, and D is a smooth anti-canonical divisor. So we know D is a Calabi-Yau threefold by adjunction. So because we are talking about this relative theory, we want to restrict sheaves from Y to D. So this is by relative theories. So we have two kinds of restriction map. So one is just a classical restriction. The other is the derived restriction, which resolve F by complex vector bundle and take a restriction. They have their own advantages. So the left-hand side is better for geometric purposes, and the right-hand side is better for this homological algebra purpose. And we want to consider F on this space Y such that these two restrictions are the same. So this is, we call this a relative condition. Let's take, for example, that the F is an ideal sheaf of a subscheme C here. So this picture is a Y is a fourfold, D is a divisor in this fourfold, which is our Calabi-Yau threefold. And then we consider here, this, for example, a curve in this fourfold Y. And then this relative condition requires that this curve has some intersect this divisor D in some nice way. And then this force that the moduli of such F does not have components. So the solution is that we should consider the so-called expanded pairs on these configurations, which we take the origin of Y, and we want this curve just intersect this divisor not in a good way, then we just do blow up, and we keep adding these bubbles, where this bubble is the projective bundle over this divisor D, and then we consider configuration of this curve in this expanded pairs. And now the thing is that if we fix topological data like curve classes, so we only need finite number of these bubbles, so we can stop at finite number of steps. And Jing Li and Baosong Wu, they develop a moduli theory of such sheaves on expanded pairs with relative conditions on this divisor D. And then there's a restriction map from this relative moduli to this moduli of sheaf on the Calabi-Yau threefold D. Simply just intersect this the sheaf with this last divisor D. And moreover, this moduli is proper if Y is proper, and if it's equivalently proper if Y is equivalently proper. So now, given this restriction map, this relative modular sheaf on Y on fourfolds, restrict to this modular sheaf on threefolds, and recall that we always assume this talk that this is a global critical locus from this smooth variety W. And now the question is about this relative theories, whether we have a natural map from this Venetian cycle shift homology to Bramall homology of this to this fourfold moduli. And this is related to a conjecture of Joyce. And similarly, you can consider a case-theoretical version, because this is a global critical locus. You can consider the analogy of this Venetian cycle shift homology, which is so-called critical K-theory, is defined by the concentric group of the matrix foundation category of this smooth variety and this function phi to this K-theory of the fourfold moduli. And because we have a properties in the right-hand side, we can take a push forward to a point, or equivalent push forward to a point, and obtain the evaluation of states on here. So we have a map from this vector space to Q. Okay, so now the question is whether we can construct this map here. sorry, this map here. So this is the difficult questions. And the thing we can do is we can do certain approximation by algebraic cycles, as I will explain here. So let's consider the zero locus of this function phi, denoted to be a z phi, with this close embedding to the ambient space. So we know that there's a Milnor triangle relating this nearby cycle functors, vanishing cycle shift functors, and pull back to the zero locus. And this gives you the canonical map from the Bramah homology of the zero locus to the vanishing cycle shift homology. So because now we are in the algebraic geometry setting, so we also have a child group of algebraic cycles on this zero locus. We have a cycle map from this child group to the Bramah homology of the zero locus. And we can consider the composition of these two maps. It gives you basically give you the algebraic cycles on this vanishing cycle shift homology. So there's a case theory version by the following equivalence of categories. So the right-hand side is the matrix factorization categories of this smooth variety W with function phi. And the left-hand side is the so-called singularity categories, which is a direct category of the zero locus modulo this perfect complexes on this zero locus. So this equivalence by the work of Orloff and this BFK in more general setting. So now we consider the Grothendieck group. We can obtain a surjective map from the K0 of this zero locus of phi to this critical K theory, to the K theory of this matrix factorization categories. So now the point is that in this critical K theory or this vanishing cycle shift homology, homology here, we can take states from here coming from algebraic cycles, from child groups, or from this K theory of this zero locus. So if we replace this critical K theory or vanishing cycle shift homology by this two space, we can define the natural pullback map. So which says that we can have a construct a natural pullback map from the child group of zero locus of these functions to the fourfold moduli, the child group of fourfold moduli, and similarly for the K theory. And they satisfy natural functorial properties, which you use to prove gluing formulas. So let me give some key features about this about the theorems. So the first is that because now we are in the very high dimensions fourfold case, we need a framework of shifty sympathetic geometries. So which in this case we consider as MD, which is global critical locus, and the derived critical locus has a so-called -1 shifty sympathetic structures, and it's mapped to this natural map to this ambient space has a shifty Lagrangian fibration structures. And moreover, this fourfold moduli restriction to this modular shift on this Calabi-Yau fruitful D has a Lagrangian structures. And if you compose this Lagrangian and Lagrangian fibration, then you get -2 shifty sympathetic structures from here to here. So the point about -2 shifty sympathetic structures, it has very special obstruction theory in the sense that the obstruction bundle has quadratic form. And then we can use the so-called SONC, this characteristic class of. Yeah, so.
What does it mean to have a -2 shifted symplectic structure on a morphism? I thought you have Lagrangian structures on morphisms.
Yeah, so it's the same. So it's considered replace the tangent complex by the relative tangent complex. Then you can formulate everything using this. Yeah. So you can. So the special obstruction theory here is enables us to employ this SONC characteristic class of Eddington and Graham, and which is localized to isotropic sections by the work of O. Thomas, and this done this there's a family version by the work of Hendrell Park. So and then having these relative theories, we can formulate gluing formulas. So in this picture, we consider a degeneration of Calabi-Yau fourfolds, where these generic fibers are smooth Calabi-Yau four, and this central fiber is a glue of two fourfolds along this common anti-canonical divisor D. And the statement is that there's a gluing formula relating invariance on the generic fibers and the relative theory we just talked about. Okay, so let me give some examples. Yeah, please.
So
yeah, I mean this child group version. Yeah, child group of zero locus. Yeah. So the first application is that we consider the simplest Calabi-Yau form, which is this affine space C4, and we consider the simplest non-trivial example of modular sheaf on this C4, which is Hilbert scheme of points on C4, and C4 is non-compact, so we need some torus action to make it proper. So the torus is similar as before. We consider this C star 4 acts on C4 by standard actions, and we take a Calabi-Yau subtorus. This T1 times 2T4 equals to 1. So we preserve holomorphic volume form C4. And then we can consider the torus fixed points of these Hilbert schemes, which in this case is not 3D Young diagram, but it's a 4D Young diagram. You lay boxes in 4D space. And in the language of combinatorics, this is also called solid partitions of size n. You like n boxes in this 4D space. So the combinatorics of this solid partition is very difficult. And at this point, still, there's no closed formula, even conjecturally, for their cons. And McMahon himself gave a wrong guess, 1915. So now the point is that because we are in the Calabi-Yau 4 case, we can consider this DT theories and this virtual class here with equivalency with respect to this torus T. So the virtual dimension here is positive. And it's good to put some insertions. So here the insertion we take is we fix some line bundles, which is T equivalent line bundles on this C4. And we consider topological bundles on this Hilbert schemes, where the fibers at each point is just the section of this, the bundle restricted to this zero-dimensional subscheme Z. So by Riemann-Roch, we know this is always n dimensions because these points, there's no high cohomology. So now we have cycles of complex n dimensions, and we have complex rank n vector bundles on these Hilbert schemes, on these cycles. We can take Euler class and integrate. So the following theorem give a close evaluation of these integrations. So the left-hand side is equivalent Euler class of this tautological bundle against this equivalent virtual class, and we take a Jenisin series. So the right-hand side is a closed formula, where the base is the McMahon functions, which is the partition function for 3D Young diagrams, and the power is the third equivalent trend class of C4 times the first equivalent trend class of this the insertion we take, the line bundle L. So the proof, for the proof, we use this gluing formula we developed, I just said, and also similar pole analysis as this work of Marlin, Nekrasov, Okunkov, and Pandarapanda on free folds. So I give several remarks. The first is Nekrasov conjecture a case-theoretical version of the Bao formulas, and work in progress of Martin Ku and Renomo. They prove it by the so-called factorization sequence of Okunkov. So the advantage for us is we have degeneration formulas, so we can compute this also relative theories and also the absolute theory for all log local Calabi-Yau curve, so which is total space of direct sum of line bundles on curve C. But we don't need a curve to be toric. The curve can be arbitrary genus because we have degeneration technique. So let me give a second examples of applications. So the example is we consider the P1 and consider the direct sum of free line bundles on this P1. So this Y is now the fruitful. And we consider a divisor D in this fruitful, which is the fiber of this map at the n smooth points, P1 to Pn, the fiber of this map, which is the joint union of n copies of C3. So if we impose this log Calabi-Yau condition, that the sum of this degree is n minus 2, n is the number of C3. So this D is an anti-canonical divisor of Y. So this is a log Calabi-Yau 4 pair. And recall that we have this restriction maps from this fruitful moduli to this fruitful moduli. And considering suitable stability, such map has components given by this the following map. So the left-hand side is the so-called P1 parameterized cosine maps from genius 0 cosine maps with unmarked points. And the right-hand side is just Hilbert scheme of points on this divisor D, which is the n copies of Hilbert scheme points on C3. So a close point of this map looks like this. So first of all, a point here is given by a map F from this configuration of rational curve to Hilbert scheme of points on C3. And this rational curve has a distinguished component here, which is isomorphic to the P1, which contrasts all other rational tails. And it has two special points, P1 and P2. Let's say n equals to 2 case. We can evaluate at these 2 points to go to Hilbert schemes. And this is the restriction map. You just given this map, and you can evaluate at these 2 points. You get 2 points in this. You get a point in this Hilbert scheme of points. So in this case, the above relative 4D theory defines a Gomorphitan type invariance for this Hilbert scheme of points on C3. So I want to say that this is non-trivial in the sense that when D is bigger than or equal to 4, this is a singular space. So it's not clear how to define Gomorphitan theories before. The next result says that we can do much better, not necessarily Hilbert scheme points on C3. We can do for any quiver with potentials or critical locus in a GIT quotients and define the Gomorphitan type invariance for such critical locus. And then the remark is that first remark is that this gives at least one mathematical approach to this partition functions of this so-called 3D n equals 2 supersymmetric gauge theory, because now it's n equals 2 because we consider critical locus instead of this holomorphic symplectic varieties, and also relevant to this so-called gauge linear sigma model, which relevant to this after the work of Witten and many mathematicians here. So secondly, such partition functions can be used to extract information of this quantum group actions on this the state space, this radiation cycle shift homology, along with these ideas and works of Okunkov's group previously on Nakajima quiver varieties. So if you start with a Nakajima quiver, you can always make it to be a quiver with potentials by adding a loop at each circle vertex. So Nakajima quiver varieties fits into this quiver with potential framework. And finally, I just raised this question, and the interesting direction to consider is there should be a stable envelope, or maybe the question is whether this stable envelope construction of Mali Okonkov and this ageneric Okonkov for not just Nakajima quivers, but for quiver with potentials. And the interesting question is whether such theory exists and whether it has connections to the above invariance. Okay, I think I'm a little bit fast, so let me just stop here and just wait for questions. Thank you very much.
Okay, thank you very much for a nice talk. It was indeed a bit fast, so we have time for questions, so please.
When you say Gromov-Witten type invariance, what exactly do you mean by that?
So say again?
Say Gromov-Witten type invariance for the Hilbert scheme. What exactly do you mean by that?
Yeah. Yes. So let me go back to here. So if you look at here, so the Hilbert scheme of points on C3 is a global critical locus. So you can view this as just standard cohomology of so let's say so when phi is equal to 0, this is just the ordinary homology of cohomology. And then if you have this map, you can just push forward this moduli to a point, and this gives you an evaluation of states. So this basically, if you insert this as a cohomology insertion, you get this Gromov-Witten invariance. So the point is that if you have this map, you can push forward to points, then this gives you Gromov-Witten theory, in this sense. Yeah. If you view this as state space, you have curve counting.
Okay, thank you.
Yeah.
Any other? Yeah.
Can you clarify? Here you've written the critical cohomology, and at some point you start instead using Borel-Moore homology of the zero locus. Are you working in some setting where those are the same, or what exactly is the situation?
Yeah, so that's a very good question. So in general, this canonical map is you don't know this is isomorphism. Sometimes it's even 0. But for example, in some high spin case, this is isomorphism. But in some case, this is not isomorphism. So the point is that if the states come from algebraic cycles, so you can define it using algebraic geometry. Yeah. And if you consider this GISM case, some people study so-called narrow sectors, which are algebraic cycles. So essentially, they come from this map. If you consider K-theory, this is better, because in the K-theory case, this is always surjective. So all states, they come from the zero locus. So in a way that if we construct, if you can show that this perfect complex go to 0 under this map, so you can descend this map to this critical K-theory. Yeah. By any case, so there's a map here, so you can evaluate all the states. You can consider K-theoretical Gromov theory for all the critical locus. Yeah. Is that okay?
Other questions? I have one.
Okay.
Do you have any thoughts on the high rank theory?
High rank, yes. I think one difficulty of high rank is about these degenerations. So the theory of Li and Wu, they only work for rank 1 case. Because if it's a rank 1, if you restrict to divisor, this is automatically stable. But if in high rank case, it's more complicated. So it's certainly interesting to consider high rank, but it's too difficult at this point. Yeah.
As another question.
So in one slide, you have this quiver diagram.
Yes.
So
yes.
can you elaborate more on how to connect those? Yes, right. How to connect this quiver to the Young diagram or the solid partition, and also.
This is plane partitions. So first of all, the critical locus is Hilbert scheme of points. So you can consider this not this diagram, but with two loops. Then this is a Hilbert scheme of points on C2 case, and in there you can also consider torus section, and the fixed point will be so-called partition, just a partition of a number. You decompose a number into this For example, 4 equals to 2 plus 2, 1 plus 1. So in this one-dimensional higher case, you just replace this one-dimensional partition by this two-dimensional partition, which in Young diagram is raised 1 dimensions, because partition goes to Young diagrams, but plane partition goes to 3D Young diagrams. So that's a precise analogy here.
Okay. There's a question there.
I suppose it's just a comment. So there's a class of 3D n equals to 2 theories for which the whole story of 3D mirror symmetry should generalize, and in particular also the relation to geometric representation theory. So
yes.
It sounds like the technology you're developing is just perfect for that. In particular, they involve introducing potentials to the n equals to 4 story. So it's wonderful to develop this.
Yeah, thank you. Yeah, I think it's very interesting to see whether you can incorporate this potential into this mirror symmetry perspective, 3D mirror symmetry. Yeah, but
For a special class of theories, yes.
yeah, but at least I don't. I think it's I don't have any idea anymore. Yeah, we can talk.
Basically, very surprising thing that 3D mirror symmetry would extend in a nice way to a class of theories, but it does, with relation to representation algebras.
Okay.
Not ordinarily algebras, as for n equals to 4 case, but really super algebras. It's actually not known to mathematicians.
Yes.
But there are physics predictions. So.
Great, thanks.
Okay. So if there are no further questions, we can thank the speaker again for the nice talk.
We have a coffee break now, and we will come back at 11:20.
Yeah, I saw another question from there.
Oh, sorry.
Anyway.
One more. After the coffee break. Yes.
What is the problem with the higher rank case? Can you please elaborate a little bit?
Yeah, the high rank case is
You mean the vector bundle case, right?
It's about these degenerations. So in higher rank case, if you restrict to divisor, it's in general not stable. So it's become more complicated. It's about stability. Yeah.
Okay.
Yeah.
It's about stability.
Yes.
So what kind of stability?
For rank 1 case, any stability because it's rank 1. So for high rank, it depends on quantity.
Le slide caricate in un unico file.
Forse in realtà è meglio usare questi microfoni perché o riusciamo a fare il cambio microfono velocemente. È meglio usare. Io sto qui in basso. Ci sono già. Quindi questi, e poi per le slide c'è un pointer avanti, indietro, e questo è elettronico.
La domanda era più sul microfono, se era.
Sì. Tanto saranno già, no, sono vari PDF, quindi bisogna che lo cambi.
Che è tutto un unico file, che basta continuare a schiacciare. Quindi nel principio il primo speaker può dare tutti i talk.
Ah, ok, può farli tutti lui.
Vabbè, meglio. Deve essere un file Tuesday.
Ma come sia? Ok.
Io qui non so toccare.
Vabbè, io andrei a fare il coffee.
Andiamo a fare colazione. Non so se l'hanno già messo su.
Probabilmente è già finito.
Yeah, I think so. It should not take one. It's too difficult. No, the one difference is that because in a fruitful case you also have single DT here. Putting one is not far from each other. Why? So in fruitful because the DT counts, the DT weights is not far from one. That's why it works. On fruitful case it's only
So I was wondering, so you have this, yes, I was wondering if you have to do that, like to avoid to be like so like because like in general like you could like imagine like it would find like this for you have this assumption that okay, like I imagine that you expect that in general like this formula.
Yeah, but it's that's right, but it's yeah, I think it's much more difficult. I don't know because
The point that the general like the point that the general choice conjecture that you have to do enough to good morphism which are like in the dark category, not in the abelian category, so it's why it's difficult. But in some specific situation you can like restrict to some abelian case where you have just to glue a thing in one. For example, to glue like the coa for Categorical threefold, it's possible like to reduce to some.
just directly attack those capabilities.
No, exactly. No, I think that just that just conjecture in general, so it's really hard. But like, yeah, I think in most like of the relevant case.
Yeah, that's. I think that makes things uncomfortable. Find something which I don't know. It's, yeah, at least I always consider global critical. I cannot say anything. The point is that if you have global critical locus, you can consider.
Okay, so even your results when you have like no physical locus like make no sense. Okay, so yeah, so in this case.
And or non-chain sign.
Yeah, I mean, so you know the modular space of it's basically we enter the question in the wrong direction. 2 seconds, I need to rephrase in my head. So we take a Euclidean three manifolds. We define a Chern-Simon invariant on it, and we look at the flat connections, right? F equals 0.
Okay.
You are basically the set of all flat connection, they give you a modular space.
Okay.
Right, and this modular space, we want to understand what is it basically describing. Is it trivial or is it not necessarily trivial? Like, because, you know, when you take SU2, you'll end up with, like you said, the floor, like a stuff with floor homology. So we want to understand what happens with U1, because I mean, we couldn't find anything
I think
on modular space. Is it trivial? Because of
rank 1 case, it should be trivial.
like how trivial it is.
It's just a line bundle.
Right?
It's just represent. I think this is representation of pi 1.
Yes. So you map pi 1 to U1. Yeah. But
let's say that we have a stack and then you have a path and later on these are three hypersurfaces.
Okay. What are you drawing now? Sorry.
So these are, okay, I will show you. These are B fields. They're not. So the two parts of the hypersurface, it's B.
Okay.
Perfect. So these pants that you can see now, they evolve in this four manifold. The hypersurface, the four manifold is defined like this more or less. So I'm taking the hypersurface, spatial hypersurface. So the knots now are B field that are closed. So you have a critical point. Perfect. So the moduli space that we are looking at is a set of critical points.
But this is a real function.
Okay.
It's not complex function.
This is a real function. So my question would be like, if I have here another critical point from all the stuff, is my set that now is 2 points? So I am this set. We have, yeah, for example, for this hypersurface, hypersurface 1 alpha. So this is from 0 to 1, exactly. This is alpha, okay? So would you agree with this picture?
I don't know. It's,
so in a sense,
I have no idea about real case. I'm more familiar with complex case.
That's fine. Okay, complex case. Okay.
Yeah, I'm more familiar with
But
Calabi.
does it sound correct? There's no problem. We don't want to put you in
I cannot judge. No, I don't know.
There is no problem. Okay, but yes, on each hypersurface there is a.
Are you physicists or you are physicists?
So for that reason, we want to double check. You know the moduli space. You know the moduli. It's more mathematical. So
you probably know.
Yeah, home of Taiwan. That's right.
Well, both conjugation, but they're trivial, so roughly speaking.
Yes.
This is a set, no?
This is a set. So what you have usually is you have, say, A, and these are given by e to the I A, and A is, say, real in pi 1 sigma, but I can do A plus 2 pi n, so I will basically get, in the end, a Pontryagin dual.
Okay.
Right?
Okay.
So what I'm trying to understand is this basically a trivial thing? If, for example, I take sigma to the S3,
okay.
Then my maps are trivial, right? So I'm trying to understand, but then I don't get U1.
So we have a physical intuition.
Or do I get a trivial representation in there? So I want, and also, like he drew, you have these pants.
Trivial case, just U1. So Hall. So this is the point.
Right.
It's not this one. I think this is wrong.
Okay.
If this S3,
yeah, this is wrong.
It's just one.
This is Hall from point to. This must be a group Hall, right? So that means this is a group with unity 1. So this 1 has to map to 1. There's no choice. Hall must be just 1 point.
Okay. Okay.
So we cannot have 2 points. Two sets.
No, S3.
S3. No, these are S3 and then.
Take S2 cross S1 is a different story. There you will have here a Z. Pi 1 of S2 cross S1 Z. Yeah, so you basically map integers to representations of integers into U1.
Yes, but for S3, because these are all S3, and my D field, I want to see the topological. I mean, so we are from the physics side.
I don't know. Yeah. Yeah. It's not key. Yeah, if you have a B field, it's this different. It's not this. This is just flat connections without B field.
Yeah, but the flat connections are the B fields. Like
So
you
B
basically
equals
have
zero.
this in the end. These are called magnetic nulls in physics, but I don't care about. I don't care about magnet. By the way, I don't care about magnetic nulls. I want to understand just this. What is this doing? Basically, that's all I care. He wants to
So
understand.
this is a point, basically, the same cluster.
That's three cases.
Okay. Fine. So basically the problem is, so you have these bands evolving in hypersurface.
What?
If I may ask, it is not a problem. Okay. So basically you have these hypersurfaces.
Okay.
And you have an F in 4D. And this 4D is sigma cross R and sigma is R. So this is ADN splitting, right? So basically our F on the hypersurface is actually B, is a curvature, for a billion it's an electromagnetism. So we're looking to the topological evolution of these B fields, but at some point there will be a critical point. So the idea is basically to take the Shensen as a Morse function to find this critical point. So we were looking to this map. Exactly. So it says that should be a point. It's homomorphic for S3, but these are all, let's say, they're all S3.
They just said, yes, P1 of S3, like it's trivial.
Yes. But if you take, for example, a non-trivial sigma like S2 cross S1, you get, for example, Z.
Yes.
Yeah, right? And so it should be basically the Pontryagin dual on the right. So my question would be, in his perspective, this path seems to evolve, right? So to me it looks like there's a coordinate here.
Yes.
So and there is a critical point here, right? Which basically tells you that from this initial to this final sigmas, three manifolds, my critical point somehow appears and then disappears. So in a sense, the moduli space is variable. It's changing. Yeah.
Sigma is a trivial.
Yeah, sigma is a three manifold, Euclidean three manifold.
Okay, so we are in four
Yeah.
dimensions.
But the problem is, so from the physics standpoint, I want to understand if basically the moduli spaces is looking to all the critical points. Hypersurface, for example.
Each hypersurface should, yes.
So that's two. So is this going to be a set of 2 points?
Just wanted to discuss.
Go. There's no problem. Fine. Thank you.
对，我考虑的什么是说但是当我一本这样也可以其他，当我入选自己进化的时候，是首先就有R3的理论叫做简化，你如果没有 R3 理论，当然把理论放西马克思。因为主要是先定了然后再做的这个理论。R3的理论上是只能做的。但我知道你单纯西马克思做这一计算也能得到结果，而这个结果受到一些数学要你说后面因为昆汀这个例子很多了，就他们做 GSM， 然后包括很多的专家是嘛。说的是 K 反口，就是口头分析。对，我不是要考虑。那个例子，我 point 主要的 point 是因为要讲很快的。modular 系统的可能。target 不是它的 frame， 而是上面的 module 这个是 highly singular。分体的形式。我的这个 target， 对，我的 target 是 highly singular。在上面做可能回来。我相信英语家是这个。对啊，就是你看这个 curve map 干嘛说对modular 系统基本在于是一个 formal 的 modular。所以 formal 给你看的给你的东西就是它比较废的 modular 系统。我们会就是把 curve map 到一个 smooth morality。现在假设你的 smooth morality 不 smooth， 是一个 modular。curve map 就去。整个好像相差很近，如果一样的
不懂物理，我不知道物理。point 是说这个数学倒是可以 formula。哪有同学呢？没有见过，没招过。没有啊。不是这个名字。我今年没有去啊，我去年去了一次，他就怕我这个 meeting 是吧？今年去了。半小时就结束了。
Hi, hi. How are you doing?
Go ahead. I need to put the microphone on or just switch?
So no, we thought that so we will use these microphones because it will be quicker to switch. So perhaps if you can be a little bit close. I mean, you don't have to be extremely close, but yeah, maybe just here in the middle. And so you are the first one?
Yes, I'm the first one.
Okay, yeah, I just wanted to check if there are all the... Oh, okay, so they are one on top of the other, okay. Okay. And yeah, so you can go forward and backward, and with this one,
It's a pointer.
yeah, you don't have to point. I mean, you can point everywhere you want. You see, it works anyway. You can point wherever you want. It doesn't matter. If you keep it pushed, this one, it goes out of the full screen.
Oh, I see.
So don't keep it pushed.
I see.
But this one, yes. Okay, so we will use the microphone there. Because otherwise putting the microphone is too long.
Yeah.
So just, I mean, if you stay here in the middle, because these two will work. So don't be, I mean, if you are here, they don't listen to you.
Okay.
Try to be here.
And,
Yeah, this goes
next
forward,
and
backward, and if you keep it pushed, you have the point.
okay.
Yes. Microphone.
It's for minutes, remaining minutes.
Yeah, it should be 8 minutes plus 2 for questions. So I will go in like with that.
Okay, thank you.
Go ahead.
Thanks.
But okay, let's start again now with the contributed talks. The first one is by Zhengping Gui, trace map on the chiral Weyl algebra. Thank you very much.
Thanks for giving me this opportunity to speak here. Today's talk is based on a paper on archive with the same title. Today I will introduce the notion of chiral homology, known as derived conformal blocks, and I will explain the constructions of trace map on chiral Weyl algebras. So the space of conformal blocks is one of the main objects in study two-dimensional conformal field theories. And today I will try to explain the space of derived conformal blocks in mathematical literature known as chiral homology. And the usual conformal blocks or co-invariants are the degree 0 part. So there is a kind of sequence of vector space. And here I will briefly review recall notion of chiral homology introduced by Baines and Drinfeld. So suppose that the space of local operators in our two-dimensional conformal field theory can be described by a vertex algebra with some extra structure, say quasi-conformal. And one can have a gluing construction. We can construct a vertex algebra bundle over a smooth Riemann surface. And this bundle is a lapped D module. Or equivalent speaking is holomorphic infinite dimensional vector bundle. In our case, it's a holomorphic infinite dimensional vector bundle with a holomorphic connection. And fiber-wise, it is the vertex algebra that we start with. From left D module of vertex algebra bundles, we can get the right D module by tensoring with the canonical line bundle of our Riemann surface. And this right D module has a structure of chiral algebra structure. But by thinking of this chiral algebra as a two-dimensional meromorphic version of an associative algebra, Baines and Drinfeld construct a chain complex as a two-dimensional Kyle version of a usual Hochschild chain complex for associative algebras, and define and redefine the Kyle homology group to be the homology of this chain complex. As expected in physics by recent result of Nick Rosenbluth, there is no higher Kyle homology in the usual rational WZW model. But the following general question is still open. So suppose we have a rational vertex operator algebra, and we proceed as I mentioned in previous slides, we can get a Kyle algebra on a smooth curve. And the question is that, is it true that all higher Kyle homology vanish for this rational Kyle algebra? Beyond rational theory, one encounters infinite dimensionality of conformal blocks. The simple example is the case of Kyle bosons, and also non-zero, non-trivial high degree Kyle homology groups like general symplectic bosons. So today I will focus on symplectic boson. So consider a homomorphic vector bundle on Riemann surface X, which is equipped with a symplectic pairing to the canonical line bundle. Then the shift cohomology group of E has a -1 shifted symplectic pairing by integration along the Riemann surface. And this -1 shifted symplectic pairing induced BV algebra structure on polynomial algebra on this vector space. So we consider the Kyle Lagrangian theory with this free quadratic Lagrangian, and the algebra structure of the quantum observables of this theory is captured by Kyle-Weyl algebra associated to E. And fiber-wise, it is exactly the usual symplectic boson vertex algebra. So it's expected that the formalism of Kyle homology is equivalent to the path integral in physics. And furthermore, if we take, if our bundle comes from a symplectic vector bundle twisted by a half spin structure, then the Kyle homology of this Kyle algebra form a D module on moduli space of bundles, which quantize the Gato Lagrangian inside Hitching moduli space. This Lagrangian is studied by Gato, Hitching, Ginsburg, and Rosenbluth. And here is the main result of my talk. So the previous path integral can be made rigorously and explicitly to a trace map from a Kyle chain complex to a BV algebra. And furthermore, this trace map is a chain map if we equip this BV algebra with its BV differential. And here there are a few points I want to mention here. Is that from this computation, a Kyle homology can be computed as a BV cohomology of this finite generated BV algebra, and it's concentrated in this special degree. So whenever we have, our homomorphic vector bundle admits a non-trivial homomorphic section, the Kyle homology, we only have a higher non-trivial Kyle homology in non-zero degree. And the same method applies to Kyle bosons and symplectic fermions have infinite dimensional Kyle homology group. And also variation of analytic torsion can be expressed as trace maps of some current insertion. And it's also possible to generalize this formulation to nonlinear symplectic bosons, such as Kyle differential operators, and extend the Witten genus to high genus curve. Thank you.
Question? Where's the question?
So how exactly would you extend the Witten genus to a higher genus curve?
Yes, it's kind of work in progress, and it's a globalization procedure. So here, a Carl-Weyl algebra can be kind of considered as a Carl differential operator on a fine plane, and there is a growing procedure, but there are some analysis in anomalies. It's kind of work in progress.
Okay.
Okay, so let's thank Gve again for the talk. Very well. Next contributed talk is Alessandro Giacchetto on resurgent large radius and symptotics of intersection numbers. Thank you very much.
Thank you very much, and thank you for the possibility to speak. So before talking about large genus asymptotics of intersection numbers, let me start with a toy example. So suppose I ask you to count the number of arrangements of m distinct objects into m distinct boxes. And the possible answer to this question is given by the factorial, m factorial. A nice thing about this answer is that this is an exact answer, but it's also recursive. So a possible way around this is to use Stirling's approximation formula, which now has the advantage of being a closed form expression, but it's only asymptotically exact. And you can even improve this answer with some subleading corrections to the formula. And so in a sense, these two answers, they kind of complement each other. Another situation that is similar to this, but much more complicated, is the one of intersection numbers on the moduli of curves. So for today, we'll just focus on psi-class intersection numbers. So the only thing that you have to know about this is that these are interesting numbers that appear both in physics and math, and they are parameterized by an n tuple of integers, d1 up to dn, that they sum up to 3g minus 3 plus n. And so a solution to the problem of computing such numbers was conjectured by Witten and proved by Kontsevich in the early 90s. So the recursive formula is this one. You don't have to understand anything about this formula except for the fact that it's a recursive formula. And it's recursive in 2g minus 2 plus n, the Euler characteristic of the surfaces parameterized by these numbers. And I should also say that this is just a rephrasing of the Virasoro constraints for this problem. So in a sense, this is a kind of the analog of the recursive definition of factorials. So a natural question would be, what about the asymptotic formula for these numbers? And today I will just focus on the large genus asymptotic formula. And the answer is given here. So it's a closed form expression. It's not recursive, and it has three building blocks. There's a constant term, this 2 to the n over 4 pi, a factorial term, gamma of 2g minus 2 plus n, and a power law, is 2/3 to the 2g minus 2 plus n. The proof of this formula was given by Agarwal in 2020, and a second proof came in 2021. And in both cases, the solution, the proof of this formula is a combinatorial analysis of Virasoro constraints by Agarwal and the determinantal formula by Guo-Yang. And the question that I want to address today is, well, first of all, is there a universal strategy to attack these sort of problems? And the reason is that, well, here I'm just focusing on psi-class intersection numbers, but there are many more problems that have the same kind of structure for which the large genus asymptotics is not known. Think about Weil-Peterson volumes, for example. A second question is, what about the geometric meaning of this formula? So, for example, here you see this 2/3. Where does it come from? And the third question is, what about the subleading corrections to this formula? And so the answers we gave to these questions are the following. Everything essentially boils down to the strategy we implemented to attack this problem, which is a combination of resurgence and the determinantal formula. And the geometric meaning of all the ingredients appearing here is, well, for psi-class intersection numbers, is given by these airy functions, which appear in this specific case as essentially the quantization of the underlying spectral curve. And with this strategy, we're also able to say something about the subleading corrections. And so the answer, I like to present it in this way. So I like to think of this formula as a kind of universal formula with some model-dependent ingredients. And for psi-class intersection numbers, these are this global constant S, which is equal to 1 in this case, but its geometric meaning is that it's the Stokes constant underlying the airy differential equation. This A equal to third is just the constant multiplying 1 over h bar in the asymptotic of the airy functions. And lastly, these subleading terms, they are computable. They're very complicated, so here is the first one, but with our strategy, we're able to say something about them. So in the remaining part, I just want to say something about the strategy. The first thing is about resurgence, and the idea, it's pretty simple. Imagine you start with a divergent series, phi tilde, and suppose that after Borel transform, you only have finitely many log singularities, which means that you have a log multiplying a holomorphic term that I like to write as a Stokes constant times a holomorphic term that you can Taylor expand. And once you know all these ingredients, you can just write down explicitly the asymptotic for the coefficients of the initial series. So you can see here it's a very explicit asymptotics given in terms of all these ingredients here. So the upshot is that as long as you know this Borel plane singularity structure, you can extract the large genus asymptotic, the large order of asymptotics. And the reason why this is relevant is that first of all we have a nice source of Borel plane singularity structure, which is this exponential integrals. And the second fact is that Borel plane singularities, they behave well under sums and products. And we implemented this strategy for psi classes intersection numbers in this way. So first of all, you can take the generating series of these intersection numbers when n is fixed. So this is the endpoint function. And there's a formula that gives you this endpoint function in terms of a sum over permutations of the symmetric group involving airy and Berry functions. So this formula is kind of complicated, but it's just a sum, and it's a sum and products of airy and Berry functions. And the upshot is that because we know everything about airy and Berry and everything behaves well under sums and products, we are able to understand the singularity structure of this endpoint function. So here are all the data that you essentially need to just write down the large genus asymptotics of the coefficients of this series here. And well, this was just one example. The main point of this strategy is that it applies to many more examples that have the same structure. So just to mention one, this is Norbury's intersection numbers that are relevant in Superval-Peterson volumes, or JT. And the formula is exactly the same. The only thing that changes are some model-dependent ingredients like the Stokes constants and the instanton actions that in this case are the ones associated to the quantum curve for this problem, which is the Bessel ODE. And this also applies to a much more complicated example, like with an R-spin intersection numbers, where again, I mean, the formula is much more complicated, but it has the same structure with some model-dependent ingredients that are related to this R-airy ODE. Thank you very much.
Microphone is coming.
Also, this local Calabi-Yau can be solved by these topological recursions. Is there progress on, or from this point of view, is there progress on getting the asymptotics, let's say, for local P2 or something?
Yeah, so no, and the main reason is that I don't know if there's a determinantal formula for that specific problem. If there is, in principle, one can try to attack it using this strategy. But yeah, I'm not for sure. There are some determinantal formula for Gromov-Witten theory of P1, but I don't know about Calabi-Yau threefolds.
Local P1?
I think just no. I think just maybe P1 with point insertions. I think, but I'm not sure. Something like this.
Thanks, nice talk. So related perhaps to the previous question. So the Calabi-Yau y squared equals to x plus deformation plus a uv equals 0 is a local description of the same model you're describing. In that context, the topological string has deformation, the Nekrasov deformation. So there are two parameters. The limit that corresponds to the wave function you wrote down is Nekrasov-Shadashvili limit, where you get this wave function solving this. First of all, do you understand why you should be in the Nekrasov-Shadashvili limit to describe these intersections? And secondly, what if you talk about the other parameter and how does it show up in your calculations?
Yeah, to be honest, I have no idea. I don't know exactly. No.
So to run your argument, do you need this a topological recursion, or is it enough to know that you have quantum curve, which annihilates?
So you need two ingredients. You need a determinantal formula, which in many cases is a consequence of topological recursion, or it's a consequence of integrability. And the second ingredient is the quantum curve. So you need both. And about the quantum curve, you need to know enough about the Borel plane singularity structure of the solution. That's all you need to know.
Okay, then let's thank the speaker again for the nice talk. And next, we have Veronica Fantini, who will talk about modular resurgent structures and spectral traces of local P2.
Thank you very much for the invitation. And I will discuss part of a joint project with Claudia Rella. So to begin with, let me remind that the theory of resurgence is very useful in order to study perturbative expansion, because it allows to compute non-perturbative subleading order contribution. And indeed, it has been extensively used also in topological string due to the work of many people also present here today. But sometimes it's interesting to study the resurgent structure of an asymptotic expansion of a given analytic function, because in that case, it might happen that the resurgent structure knows more about the structure of the function. And that is the case, for instance, of the first fermionic spectral trace of local P2, because as I studied in the joint work with Claudia, we proved that the generating function of the Stokes constant are holomorphic quantum modular forms. And even more generally, we introduced the notion of modular resurgent structure that are conjecturally supposed to encode describe holomorphic quantum modular forms. So the first fermionic spectral trace we consider are the one that arise in the context of the topological string spectral theory correspondence of Grassi and Tsuda-Marino, where a quantum mechanical operator is constructed by quantizing, okay, too fast. It's constructed by quantizing the mirror curve of a local Calabi-Yau threefold, such as local P2. And then the fermionic traces are the coefficient in the expansion at the orbifold point of the spectral determinant on the inverse operator. For instance, in the case of local P2, that's how the first fermionic spectral trace look like, in which you see the holomorphic and anti-holomorphic block given in terms of Kupo-Kammer symbol. Now, in her work, Claudia studied the resurgent structure of the asymptotic expansion of the logarithm of the first fermionic spectral trace in both the strong and weak coupling regime, meaning in the limit as h bar goes to 0 or infinity. And in this example, the resurgent structure is very simple, but at the same time rich. Because, first of all, the singularity in the Borel plane are organized in a single tower. The Stokes constant are known exactly, and in particular, they are the coefficient of these two L functions. So already at this stage, you can see that the L function have some sort of symmetries, which is even more explicit and encoded in the functional equation, which describe the analytic continuation of the 2L function. And thanks to this very nice structure, we then considered and studied the modularity property of the generating function of the Stokes constant. So in particular, our main result is to show that these are holomorphic quantum modular form for the group gamma 1, 3. And here, the modular parameter y is in fact related to the h bar constant. Moreover, that also considering the free convolution, you get other two holomorphic quantum modular form where the role of the cocycle is exchanged. And let me remind that the group gamma 1, 3 is deeply connected with the geometry of the problem, so of local P2. Now, taking this as a motivating example, we introduce the notion of modular resurgent structure, which in a sense represent and encode the one that I briefly described in the example of local P2. So by modular resurgent structure, we mean that the singularity in the Borel plane are organized in a single tower, that at each singularity, the resurgent series is given simply by the Stokes constant, but these Stokes constant are coefficient of an L function which admit meromorphic analytic continuation. And conjecturally, if a Q series has an asymptotic expansion with this modular resurgent structure, then it's supposed to be an holomorphic quantum modular form for some subgroup of SL to Z. So the message is really that this modular resurgent structure conjecturally should give rise to holomorphic quantum modular forms. And to conclude, let me give a general overview of other results that we studied in the paper with Claudia. So once more, let me stress that as evidence of this modular resurgent conjecture, the asymptotic expansion of the logarithm of the first fermionic spectral trace of local P2 in both regimes give rise to holomorphic quantum modular forms in the sense that the generating function of the Stokes constant are holomorphic quantum modular form. Moreover, that the L function play a very interesting role to describe the following feature. So on one hand, that a strong, weak resurgent symmetry is at a play, and in fact, it is responsible of describing how non-perturbative and perturbative contribution in both the strong weak coupling regime are related to each other. And moreover, we introduce a new paradigm of resurgence where new series resurge as dictated by the functional equation. As another evidence for our conjecture, we also consider examples that arise in the theory of mass cusp form. And finally, one of the other interesting questions that we can ask when we study asymptotic series is what are their summability property. And in the example of local P2, we can prove that the generating function of the Stokes constant in the weak coupling regime can be reconstructed taking the medial resummation of its asymptotic expansion. And the same result is conjectured for the generating function in the strong coupling regime. And more generally, we also expect that this result will hold every time we have a modular resurgent structure. So I will stop here. Thank you for your attention, and if there are any questions.
Two questions.
Thank you for the talk. I mean, in this work of Marcos and Jigu, they have found that the Stokes constants are related to BPS states on the local P2. Is that, and now you have a complete series of these Stokes constants. Have you an interpretation of those in this, along these lines?
We would like to, we are trying to investigate it further. It's true that conjecturally that's the expectation, so that's what we would like to prove, but so far we still don't have the exact result. Thank you.
Thanks for a nice talk. Do you have any interpretation of the modular resurgence structures in M theory or string theory in any form? What is the interpretation of these?
Oh, sorry, of what? Of this?
Embedding these questions into M theory or string theory and what they mean.
I mean, through the topological string spectral theory correspondence, the Stokes constant should be related, in fact, with the BPS state, as also Albrecht was saying. And, but so far, it's purely conjectural, and we don't have yet.
But you have a lot of structure that you have, like these forms of the functions that appear. Do you have an interpretation of their form without? In other words, can you interpret your results in a different language inside string theory?
I think through this conjecture, yes, but so far we still don't have the exact way to translate. In fact, there is maybe one thing that I can comment, is that even looking at the free energy for the topological string point of view, these are known to be quasi-modular forms for the same group. However, the parameter here for the modularity is the parameter in the moduli space that parameterizes the complex structure of the mirror. So it seems that there is some, in a sense, common structure, and maybe that's the way, that will be our approach to try to understand it. But yeah, we are working on that. Thank you.
My question concerns just to be your opinion about this statement. Okay, this asymptotic expansion. Do you think that they have any prospects in dealing with UV divergence?
I'm sorry, I don't know.
Okay, thank you.
Okay, so let's thank Veronica again.
Thank you.
And okay. Next speaker is Maximiliano Ferro, who will talk about correlators in the IBJM line defects from string worldsheet on ADS4 cross CP3.
Okay, hello everyone. Thanks to the organizer for this opportunity. I will talk about correlators on line defects in ABJ or ABJM theory from the string worldsheet on ADS4 times CP3, and in particular, I will focus on the role of the Caramon field. This is a work with a collaboration with my advisor, Diego Correa, and Víctor Geraldo Rivera, both from the Instituto de Física La Plata at Buenos Aires, Argentina. Okay, let's put some context for this work. The ABJ or ABJM model is an n=6 super Chern-Simon gauge theory with matter, which gauge group is an product of UN gauge groups. At a large n limit, this model can be considered as a description of M theory on ADS4 time and 7-dimensional sphere quotient by a discrete group. But in the Hopf limit, the geometry collapses to ADS4 times CP3, and there is a type 2A string theory description. When the ranks of the gauge group are different, we must include a non-vanishing Caramon configuration around the CP1 geometry between the CP3. This flat configuration coupled with the endpoint of the open string, and this is the key point of this work. Okay, let's talk about Wilson line as one-dimensional defect CFT. As you know, the Wilson operators are non-local operator defined along some curve. In particular, when consider lines, this curve is open. In generally, this operator partially breaks the symmetries of the field theory, but for superconformal field theories, you can consider some operator which preserve some amount of the supersymmetries. For example, in ABJM model, you can consider the 1/6 BPS, which preserve 4 of the original supercharges. This operator is given by this super connection. These lines, you can consider this line as a theory in the sense you can consider the endpoint functions along this line, and in some cases this given an conformal field theory, and the correlators are constrained from the conformal invariance. From the holographic point of view, the Wilson operators are realized by the open string worksheet, which coincide in the boundary of ADS with the counter of the Wilson loop or Wilson line. But different Wilson operator can be realized, but take different boundary conditions in the compact dimensions. For example, for the 1/6 BPS Wilson line, you need put Neumann boundary conditions in CP1 geometry. Okay. Now you can consider fluctuations around the classical solution, and for the Wilson line, the classic geometry induced in the worksheet is an ADS2, and you can consider the bosonic fluctuations, and you need to consider the boundary behavior of the fields. For example, for the massless scalar field, you have different possibilities for the boundary behavior. You can consider Dirichlet or Neumann, or some mixed boundary condition. The point of this work is the Caramon field induced and mixed boundary condition for the fluctuations around the CP1 direction. You can write the quadratic and the quartic action for this problem, for the fluctuations, and we need put an extra term for the Neumann boundary condition for the string worksheet, and couple with the Caramon field. The point is the Caramon coupled with the string as a boundary term. You can extremalize this action and obtain the classical green problem with a particular boundary condition, and we resolve this problem and obtain the green functions. The green functions contain a term symmetric and other terms antisymmetric in the worksheet coordinate, and later you need take the mean value around the directions of the CP1, because the strings are deslocalized on the CP1 geometry. For the test to test the conformal invariance of this defect, we calculate the 4-point functions at Lee in order. This is the result, but the question is to next next to leading order. This is a hard problem, but we consider the derivatives of this 4-point function, and we can extract the cross ratio function in explicit way, reveal an conformal invariant in non-trivial ways, because there are several anomalous terms, but these terms are cancelled between them. This expression is crossing symmetry manifestly. And okay, this is all. More details. For more detail, you can see our publication. We provide some evidence about the conformal invariance of the 1/6 BPS Wilson line in ABJ theory from the string worship perspective. And the next step is try to do analytic bootstrap to calculate these correlators. And other open problem is include fermionic and calculate explicitly the one loop within diagrams to more precise result. Okay, it is all. Thanks again, and ask me.
That's a question.
When you say ADS2 CFT1 correspondence in this case, do you exactly mean conformal quantum mechanics, or is it nearly CFT?
No, it's a kind of conformal quantum mechanics. But you don't know the explicit Hamiltonian of the problem. You know the symmetries along the line.
I see. So it's not like the SYK stuff.
No.
I see. Okay, thanks.
Okay, then let's thank the speaker again for the nice talk. And we continue with Ideal Majtara on the partition function of Algiers-Douglas theories on the blow-up.
Okay. Thank you for this opportunity to talk. Then we start from supersymmetric gauge theory in 4 dimensions. We know with n equal to supersymmetry, the low energy theory is fixed by the geometry of the Seiberg-Witten curve. And we are interested in particular kind of theories, the Algiers-Douglas theories, which are some strongly coupled and isolated superconformal field theories, which appear as singularities of the Coulomb range. And their characteristic is that they have mutually non-local degrees of freedom. And so they don't have a Lagrangian description, and we need different tools to study them. And one possibility is to use the theory of integrable system. And as an example, we will focus on the simplest Algiers-Douglas theory, that is the H0 theory. And so the Seiberg-Witten curve is associated to an integrable system because it's the spectral curve of the integrable system. And if we introduce now a self-dual omega background, then this system acquires a time dependence. And in the case of rank 1 theories, is given by the Paine-Levé equations. So we have the so-called Paine-Levé gauge correspondence that give a map within the integrable system and the gauge theory, and the time is the coupling scale, the Hamiltonian corresponds to the Coulomb parameters, and in the Seiberg-Witten theory is obtained in the limit in which we remove the omega background. So here there is a classification diagram of Paine-Levé equation, and one can see that there are some limits to reach, to pass from one equation to the other, and this corresponds to the RG flow of the gauge theory. And now we are interested in considering the theory on the so-called blow-up. The geometry of this blow-up is in the picture. The idea is that we remove the origin, and we replace it with a sphere, the exceptional divisor. And on this sphere, we put some surface operator, which gives some magnetic flux measured by S. Then we can define the so-called blow-up factor, that is the ratio between this blow-up partition function and the one without insertion. And we will see that this nicely maps in the integrable system, because it's the tau function of the integrable system that directly encodes, from the gauge theory point of view, information about the partition function of the gauge theory. And now, first of all, in the Seiberg-Witten limit, we have that this blow-up factor has a universal structure, because it's always given by the so-called Weierstrass sigma function, that is an elliptic function that depend on two parameters, G2 and G3, that are given by the Weierstrass parametrization of the Seiberg-Witten curve, that is this cubic parametrization. And this result is related to the integrable system because sigma is the tau function of the integrable system, the autonomous one. And more, this has also a geometrical meaning, because from Donaldson-Witten theory, the previous result can be interpreted as saying that the generating function of Donaldson polynomials on the blow-up manifold is related to the one on the blow-down manifold with a universal factor, that is this blow-up factor, that is the sigma function. And if we introduce omega background, then the Donaldson invariant become equivariant Donaldson invariants, and we have a generalization of this formula where the sigma function is replaced by the Painlevé tau function. And this can be seen using the so-called Nakajima-Shockley blow-up relations. Now, this sigma has this expansion, and which is in terms of polynomial G2 and G3. This can be interpreted physically because is a realization of the operator state correspondence for this blow-up state, in which we can rewrite it as a sum of local operators of the chiral ring that is generated by U. And the same logic applies in the omega background, so also for the blow-up factor in the omega background, we expect a structure of this kind. And so the question is now how to fix these coefficients of the expansion, and this can be done using the integrable system, because it turns out that this expansion, from the point of view of the integrable system, is an expansion around the zero of the tau function. So using plugging this kind of ansatz in the Painlevé equation, one can fix recursively all the coefficients. And in the case of the H0 theory, we obtain this relation here, and we have a recursive relation, and we can see that the polynomial have integer coefficients. And this actually, in the case of sigma, is proved, can be proved, for example, from a theory of Schur polynomials. In the case of tau, we check this to very high order, but we don't have a proof, so we conjecture that they are lower integer, and physically, we expect they to be related to the counting of BPR states. And and the other important property is the modularity. We have that this blow-up factor is a holomorphic function of U, but this has also an interpretation in terms of the topological string theory, because this tau function can be interpreted as a non-perturbative completion of topological, the perturbative topological string partition function, which arises as a kind of resurgence of it. And then one can see that this modularity property of tau directly implies the holomorphic anomaly equations. So it is there is a clear connection with the topological string. And okay, so let me conclude. As I said, this blow-up factor was studied in a particular limit, this self-dual background that actually is related to, so is a particular omega background. One can ask what happens in general. And the answer is that the integrable system becomes a quantum integrable system. So we have to quantize the Painlevé equation, and this will give the natural answers, let's say, for metrical interpretation as equivariant Donaldson invariants. And let me say that in the Seiberg-Witten limit, actually this blow-up factor can be computed in terms of the so-called U-plane integral using the low-energy effective theory. But it will be interesting to compute also this one that arises from the integrable system in terms of a quantum version of this U-plane integral, where now we have also this omega background. And finally, this modularity property may help also to fix the holomorphic ambiguity for the topological string, but this we don't know. And that's all, and thank you for your attention.
So have you tried to write down the topological correlation functions of surface operators for compact toric manifolds?
It is in the program, but for the moment we didn't try, because we first did this check, but it's an interesting question, yes.
Yes, this is working. So I guess then you know. So Yuri Nadayev and I wrote down, used U-plane techniques to write down the partition functions of the surface operators. The point operators actually turn out to vanish. But for the surface operators, we claimed it for arbitrary compact four manifolds. Your techniques should apply to the toric case. It would be very interesting to confirm or deny our results.
Yes, we have to check this, the relation with the topological string for now.
Further questions? Oh, yes.
Can you say more about what is a quantum U-plane integral?
Okay. Yeah, and this is an interesting question. Okay, let me first say about the U-plane integral. In this case, the idea is we just write the effective Lagrangian that we know, the infrared Lagrangian that we know from the Cyber-Witten theory, and then we can explicitly compute the partition function because using the topology, because this quantity is topological, we can decouple essentially all the dynamical degrees of freedom, and we reduce to some path integral over zero modes essentially. In this case, in the case of the quantum U-plane integral, we expect to do the same, but now we have to do an equivariant version of this construction. So the supercharges that we use in the Cyber-Witten case must be deformed with this parameter. We have some equivariant version of them, essentially the one that were used by Nekrasov in computing its partition function in terms of instanton corrections. And so more or less the construction will be like this, but the details for the moment we don't know. But it's a very interesting problem, we think.
Any other question? Okay, then we can thank Ideal again. Excellent timing. So now lunch is served in the cafeteria, not outside because it's raining, which is on the same floor of the terrace. And we will reconvene here at 2 o'clock sharp.
neanche se c'è la presentazione. Proviamo a uscire e vediamo se c'è. Ecco, guarda, vai su file qui. No, anche scusa, ho sbagliato. Vai sulla cartella.
so it's unmute. So
Okay.
it should work. Yeah.
Does it work? Okay.
Just for some extra power.
Okay, please have a seat. Okay, so welcome to the afternoon sessions. Great pleasure to introduce Abresh Clem from Bonn University. He's going to tell us about Calabi-Yau periods in QFT, string theory, and general relativity.
Okay, so thank you very much for the invitation to speak here. And it's of course a great pleasure to be back in Trieste. So my talk will, I don't know how long it is ago that you calculated Feynman graphs, but I'm sure you know where they are good for. So I don't repeat that. But the talk is, I'm not very long in this area. So basically, I started with some students, and then it turns out that these Calabi-Yau periods are very important, and then I could work with really people that from the Feynman graph communities have a lot of better ideas about the subjects than me. But it's basically divided in 3 topics. So the blue ones is about quantum field theory. Then also this red one is a quantum field theory. This one is more like an application to a symmetry, a Youngian symmetry problem that comes from ADS-CFT. And the last one is about the scattering of black holes. So the idea is basically that period motifs in Calabi-Yau manifolds we have studied a lot in string theory, and in particular in mirror symmetry in the B model. And so we know a lot about them, and we realize that they have new applications to these problems in amplitudes and Feynman graphs. And I organized them in the following way, the talk. So the first is an amplitude evaluation in systems with Youngian integrable systems, symmetries. So that comes basically from N=4 super Young-Mills theory, and has been formulated in a simpler fashion in fishnet series. And then the next thing is basically evaluation of amplitudes of Feynman graphs in normal quantum field theory, generic quantum field theory. No supersymmetry is implied here. And that is, so to say, important for new precision tests, maybe at collider physics. And then the last topic is even more strange. It's a completely classical problem. You want to consider the scattering of 2 black holes, real black holes, like we have the in-spiraling that you measure with LIGO, the gravitational waves. And you have also a quantum field theory approach to it in the post-Minkowskian approximation. And you also see Calabi-Yau motifs coming up in this context. So let me sort of start with an observation that comes basically from this graph. So this graph is kind of a self-energy, and it's called the banana graph. And so basically it has L minus L loops. And to this banana graph in the first paper, we could associate periods of a Calabi-Yau, and this is a period of the Calabi-Yau is a complete intersection in a bunch of L+1 P1s.
and then you intersect it you have two hypersurface constraints, so it's a complete intersection in each, which are of degree 1 in each of the P1. So that's a Calabi-Yau. And it turns out that the complex deformation parameters of this Calabi-Yau are given by the masses over the momentum, so it's a scale invariant quantity. And it so turned out that, for instance, if you take the limit that the masses are 0 or the momentum is very large, then you get to the mum point of the Calabi-Yau. And then you can, for instance, see that the Feynman graph is the maximal degenerating period of this Calabi-Yau. So it's, this is here summarized a little bit. So the observation, it's an example, but the observation was more general, that one-loop graphs basically are rational functions, and then two-loop graphs, that would be the sunset graph. If you just have 3 propagators in this banana graph, they are elliptic functions, and then you see already the elliptic curve here on the right-hand side. And then 3-loop graphs are families of K3. That is really true for this graph. And then higher loop, 4-loop graphs are Calabi-Yau threefold, and so on and so forth. And this is for the maximal cut graph of this, but the full Feynman graph has actually boundary conditions. So it has to fulfill an inhomogeneous differential equation. But the observation also is not particularly original or new. It was maybe goes back to Gelfand. And then many people, let's say in the last 10 years, like Bloch, Van Hove, Kerr, Duran, Weinzierl, they have all worked in a similar direction. But for instance, a full identification of L-loop graphs, of arbitrary loop graphs, was done in these first 2 papers that I cite here. And you see there's something which is a little strange. If you look at string theory, you would expect that maybe higher loop graphs go with a genus of a Riemann surface. So they go more, so to say, in this direction, in higher and higher genus. And this, so to say, this is a charting of algebraic varieties that was done by Kodaira. So basically, he says if the thing are Fano, then they are very simple. They are finitely many, and so on. And the Calabi-Yau case is, so to say, the critical one. And beyond that is very bad, what we understand of the varieties. And so to say, it's a little lucky that now this higher loop, at least for this graph, go just in the dimension and not in increasing the genus. So that is one of the upshot of that. But here is a little bit more complete table of what I said so far. So the maximal cut Feynman integral is related to a period integral in a geometry. So in this case, this is just this complete intersection. And then the homogeneous Gauss-Manin connection of that one determines these periods in a way. And you can also turn on a strongly motivic way. So basically, let's go first to the physics thing. So this is the actual Feynman graph is then a chain integral, also epsilon deformed, and it corresponds to an inhomogeneous Gauss-Manin connection. And I had also, of course, mathematicians stress the groups that act on this situation. And the most important groups on this Picard-Fuchs equation is certainly the monodromy group, and it's important whether they are reducible or irreducible. But if you pick a particular fiber, then you can also define the action of the Galois group, and then you can also ask the question whether they're irreducible representations, that you have attractor points and stuff. And it's also, they have a notion of extended motives for these things that are the real Feynman graphs. That, of course, gives only information about the values of the periods, or in this case, the Feynman graphs at the special fiber in the family. So in physics terms, at the very particular value of M and P, if you like. So, so this is a general picture. So I repeat a little bit what a Calabi-Yau manifold is. So, of course, it's a complex, compact manifold of complex dimension n that has 2 forms, a Kähler form and a holomorphic 3 form. And this condition that you have this unique holomorphic non-vanishing 3 form is equivalent to the fact that the first Chern class is 0, or as Yao has proven that there exists the Ricci flat metric, and also that the holonomy is SUN, and then it has 2 covariant constant spinors, and that's why string 3 mostly like Calabi-Yau. But I don't care too much because I need anyway the Calabi-Yau in any dimension. So for me, it's more, the trivial remark is more useful that this is a generalization of an elliptic curve in a sense, because if you write down an elliptic curve here, I wrote down the Legendre curve, then you have this omega just given in coordinates by this formula, and so this is the holomorphic 1,0 form, and the small omega is just the volume form. So we also know from string 3 that this C = 1 condition is very easy to control. So for instance, we can take the cubic in P2, and then we get here an elliptic curve in the Weierstrass form, and this has 1 modulus. So that would be the easiest situation, but this can be mocked up immediately. So if you take for the Fano variety with positive Chern class, you take, let's say, a toric variety, and then you consider a section of the canonical bundle, then you get in dimension 1, so this would be elliptic curves. You get 16 types of elliptic curves. They have families which different torsion, generic torsion, and then if you do this for K3, you get this many. If you do this for Calabi-Yau, Kreutzer and Skarke found this many, and a crude estimate for 4-folds would be this number. So there are certainly many Calabi-Yau, and so far my question was a little bit what a big variety of Calabi-Yau would appear in Feynman graphs. Is this always the same, or so that was one question. Another way of doing them is branch covers over this Fano variety n-fold. Then it has to be branched at a certain class of the canonical bundle, and then it's also a Calabi-Yau manifold, and we see this in the example of the fishnet graphs. Then this complete intersection that I already have here on the board, that is a Calabi-Yau if the degrees of the hypersurface fulfill a certain constraint. And then, of course, we have many other ones. For instance, we can take Grassmannians for the ambient space of Lac varieties, etc., etc. So there are many of these of examples that we can potentially identify with Feynman graphs. But what is more structurally interesting is these periods, because our claim is that at least the maximal cut integral is the period of a Calabi-Yau. And so the period is this pairing here between homology and cohomology. And what is also very important is what I call they can be viewed as a map from the homology to the cohomology group by this integration. So this defines the period. And what is also very important is that you have another bilinear, the intersection pairing, which usually is defined over Z, but you can also do this over algebraic extension. Sometimes this plays a role. So if n is odd, so if the dimension of the Calabi-Yau is odd, then you can make this intersection, pairing is symplectic. And if n is even, then you have to think a little bit what it is. So for instance, for K3, it is written like this. So, so then you can pick these cycles, the A and B cycles, and this is an SP4 choice here. I make them intersect like it would be compatible with SP4. But the good thing is, of course, this is all already visible in the elliptic curve. So here are the periods, and here here's the period integral, and here is the second cohomology element, which you can represent by a meromorphic form of this second kind, and then you get these elliptic integrals are basically the things that I'm talking about and generalizing. And this is well studied because these things solve Kepler's problem, and it also well studied in 1881 that they fulfill a linear differential equation. So for instance, for the Legendre curve that I gave before, it's this differential equation of second order, because we have two periods. So this all generalizes, but what is the decisive structure, which also plays a big role in the following of the talk for Calabi-Yau's, is that there is potential for there is a Kähler potential that can be written like that. So there is one real Riemann bilinear relation, which says that this is always positive, and it can also be interpreted as the calibrated volume of the Calabi-Yau. And it also gives the metric on the Weil-Petersson metric on the moduli space of the Calabi-Yau, which will be just as physical parameters. And the second bilinear is this one where you don't take complex conjugation. So here you take complex conjugation, get a real quantity. Here you don't do the complex conjugation, but you take derivatives of the period, and it's clear by consideration of type that this is 0 if k is less than the dimension of the manifold. And then you get actually a rational function in Z in this complex parameter if k is equal n. And you can also see that, I mean, here is essentially the justification of this formula, why it only kicks in if k is equal n, because then you reach, so to say, from the n0 form, the 0n form. So these are the two structures that you have on the Calabi-Yau. So the question is a little bit what they mean for Feynman integrals. So let me sort of say this for one parameter families. So this second equation, this was the holomorphic equation, says that the one parameter family operator is actually self-adjoint. And that is this property. And you check that, for instance, the differential operator for the Legendre curve is self-adjoint, is one of these examples. And you also have here this C again, that is a rational function. So this is how you can compute actually the C by a differential equation up to a multiplicative constant. And one very important second consequence of these holomorphic equation is that the Wronskian is the inverse of the Wronskian is actually again linear in the period itself. Also, the Wronskian is of course the derivative of the periods, and if you take the inverse of the periods, it has all rights to be of high transcendentality, but it's not. It actually is a rational function times, so these are all rational functions, times the intersection form, which is just a constant matrix, times the original Wronskian. So it not raises somehow the transcendentality. And that is very important because if you do, for instance, we have seen that these Feynman integrals are actually solutions to the inhomogeneous differential equation. And of course, if you now solve that by the variation of constant method, then you need the inverse of the Wronskian. And so you get just iterated integrals of Calabi-Yau periods and their differentials. So that is very, very important and also very similar, like you get differential equations for elliptic curves. So that's a good property. And then also you can write the Gauss-Manin connection in a preferred way. This is basically the generalization of the previous statement to arbitrary manifold coordinates. So you have this principle of doing iterated integrals for finding the inhomogeneous solution also generalizes to this case. So this is just what I said, namely that in the variation of constant procedure, you get these iterated integrals of periods and the derivative of the periods itself. And then this special form of the Gauss-Manin connection also implies that if you put in the epsilon parameter, I will explain this more carefully later, then you also get iterated integrals of periods. So now I come to the second part of the talk, namely the Calabi-Yaus that play a role in systems with Youngian symmetries. And of course, here the driving question is a little bit what is necessary to solve non-trivial quantum field series. And in the original state, that was asked for n equal 4 super Young-Wells in the RDS-CFT correspondence, and the people have found that it has a Youngian symmetry, and you expect basically that maybe by this Youngian symmetries that all the amplitudes of this series can eventually be calculated, and indeed for a little bit simplified model of that, that turns out to be true. So, so the question is whether all observables follow from the symmetries or not. And as I said, I don't do this in the original model. That is, for now, too complicated for me. So I do it in an integrable deformation, which preserves this Youngian symmetry. But in this case, I can consider a simpler series, and I can, in particular, do this in any dimensions. So let's look at this fishnet series. So this you can consider also in 4 dimensions for the original super Young-Mills problem. But here, if you, let's say, are in 4 dimensions, then the natural weight of the propagators is actually 1/2, like for the scalar, and then in 2 dimensions it would be 1/2. So these are the conformal choices, and the Youngian symmetry is an extension of the conformal symmetry, so you need a conformal series. And why this theory has so much been considered is they have the extension of they keep the extension of the Youngian symmetry. And another generalization is one which cubic interaction. You see the other one, they had actually quartic interaction here. So this one had quartic interaction, and the next one has cubic interaction. And then if you want to make it conformal, you have to choose the propagator weights to be 3/2 at each vertex. And why was this, so to say, considered anyway? Because the natural dimension is d-1/2, and then the valency for the natural series in 6, 4, and 3 dimension have to be 6, 4, and 3. And that's why these 6, 4, and 3 series are very interesting. I don't consider the 6 series so much because it turns out they are related to the 3 series in a way. But now I want to get Calabi-Yau manifolds from, let's say, a series with 3 vertices, valence 3. And I put them all in a lattice. So these are the 2 cases I really discussed. This I will not so much discuss. But the idea is now, how do you get a graph in this theory? Basically, you draw a curve, and then you get this kind of Feynman integral. But this is an integral in the position space. So these are positions. And these are external positions of the graph. These internal positions you want to integrate over. So this is, for instance, in the momentum representation, it has as many loops as you have vertices in the position graph, because the momentum graph is the dual graph. So this is the thing I want to calculate, and finally it turns out that you can associate the Calabi-Yau to this problem already. And the Calabi-Yau that I want to associate it turns out to be a multi-covering, and I explain you now how I associate the Calabi-Yau. So first of all, as we have seen, we do this in 2 dimensions. So I adapt the propagator weight so that this is a conformal field theory in 2 dimensions with a Youngian symmetry. And then I get these propagators here, and these are the ones, the internal ones, which go between two internal edges, and then these are the ones which connect an internal to an external edge. And the function eventually will depend, of course, on these external positions. And as I said, at each vertex now I have to fulfill this. You can also consider more general series which have different valency vertex, but I will now consider for now things where the valency of all vertices is equal. And now how do I associate a Calabi-Yau to this? So basically we are doing this in 2 dimensions, and the propagator weights are given by this here. For the quartic tiling 1/4, and for the triagonal tiling we have this propagator weights. And now I sort of engineer the Calabi-Yau so that its period becomes the integral I'm interested in. And how do I do that? So I take, remember that we have as many vertices as internal points, and they all live now in a P1. So I take as the base space the Fano variety of P1 to the number of vertices, and then I write down a polynomial that is precisely branched at the right degree of the canonical class. So I want to have such a polynomial, and it is branched at this thing, but it's easy to see for these triagonal and quartic lattices that is just the right degree to be the canonical class. So we have these P1s, and then we have here the hyperbolic section, then this KB, and you see this formula that makes it the Calabi-Yau is precisely fulfilled with this choice of propagators. So it is a Calabi-Yau, albeit it is a very singular Calabi-Yau. So why I'm doing that? I'm doing that because I know that the people in this Youngian, they want the amplitude. The amplitude is given by this. So basically, they want to make an integral over all these internal legs, and then they want to consider this integral. And this turns out to be up to a conformal factor, also an integral that is defined in the cross ratios, which are, so to say, conformally invariant. And all the, so to say, conformal representation is given in this prefactor. But the thing is, when I do that, and I defined my polynomial like that, then the holomorphic 3-0 form has this form, and it's given here. And you see that this piece is just omega wedge omega bar. So in other words, I have a Calabi-Yau so that my bilinear of periods calculates the amplitude that they want. And now we have a couple of observations or claims. I mean, the first, I have actually proven that I can associate a Calabi-Yau variety to each of these MGs whose periods determine the amplitude. Then the second one is, of course, also relatively trivial. The amplitude in this Youngian symmetries, these Fisher amplitudes or integrals, they're actually more like amplitudes. They have to be monodromy invariant. And you see, this is a monodromy invariant combination of the periods. So it cannot be much more than that if the monodromy is irreducible. And it turns out that this is the only single-valued expression that you can write down. So it is actually the volume of the Calabi-Yau is the amplitude in the fishnet graphs. So that's it's a nice thing. But you can ask, is this sort of, say, a more general principle, or is this just by chance? Look, for instance, at n equal 4 theory in d equal 4. Then you can look at the 4-point amplitude. And it's given by this. It's very similar. You have external legs, 4 of them. So in this case, the graph is just a cross. And you have 4 external points. And then you have a couple of conformal factor. And then the thing which becomes the volume in the case of the Calabi-Yau becomes the Bloch-Wigner dilogarithm, which is, of course, a volume of a tetrahedron in a hyperbolic 3 space. And you can more or less do the same thing that I did for the Calabi-Yaus. You can write down a differential equation so that this e to the k that I defined previously from the periods is the Bloch-Wigner dilogarithm. So that fits very nicely. So there's a more general principle that these amplitudes evaluate to volumes. Let me say something about the role of the Youngian symmetry in this construction. So, so the Youngian symmetry in 2 dimensions splits, and it makes the problem much easier. So, so first of all, it splits in 2, in a holomorphic and an anti-holomorphic part, and the holomorphic part is just generated by what you know from conformal field theory in 2 dimensions by these operators, and then I have to, in addition, create the Youngian symmetry for that. And it turns out that, of course, these are operators which act on these external vertices, and they somehow act on the amplitudes, and they have to, if the amplitude is invariant under this Youngian symmetry, they have to annihilate this amplitude. And you have to take, in addition, into account the permutation symmetries of the graph, so you get actually what we call the Youngian of the graph, and this annihilates the amplitude. And now the next claim that we have proven in many cases is that these Youngian symmetries are actually equivalent to the Gauss-Manin connection of the Calabi-Yau that are associated with them. So you have, if you have a Calabi-Yau, you get something which is called the Picard-Fuchs differential ideal, and these Youngian symmetries precisely generate this Picard-Fuchs differential ideal. So it is, in this sense, equivalent to the Gauss-Manin connection, that the periods are flat. And of course, by this token, you can calculate the period up to linear combination. And then you ask yourself, okay, I mean, now I have to build this monodromy invariant combination. So I have to then calculate the SP4Z monodromy and find this combination of the period, which is the Youngian. And this is fixed when the monodromies are irreducible up to a factor. If this is irreducible, you can have many factors, but if it's irreducible, as it is in these examples we looked at, then it's just fixed. So in other words, the symmetries and the idea that you have to construct a single-valued combination give the amplitude. There's nothing that you need in addition. And also, as in the Feynman graph community, you can ask yourself the question, can I do this integral, maybe not numerically? And you can, but it's very complicated, because this integral has an integrand that has poles from the singularities of the Calabi-Yau, and any numerical integration program will take extremely long. So it's much better to solve a differential equation than to do an integral as usual in this case. So there are also some some other things that maybe highlight my the fact that I emphasize so much the motive. So if you there is a symmetry that is clear from the Youngian symmetries, namely that is called the star triangle relation. So for instance, if you take this original thing that I had here, then this would be a Calabi-Yau threefold, but a very singular one, which in addition has a set 3 automorphism, because this is a triple covering of 3 P1s. And if you do the star triangle relation, you get actually a one-dimensional object. So in these examples, you get the motive of a singular Calabi-Yau is actually equivalent to a motive of a certain Picard curve, and you might wonder, why does it work? And it works because if you do conjugate the periods, then there are periods which are invariant and not invariant. And in this process, so here is the Hodge diamond of the Calabi-Yau threefold. So this is the 3-0 form, this is the 0-3 form. And then I grouped it a little bit into periods which are invariant and non-invariant. And if you do the star triangle relation, then you group these points differently. So you basically shift them. And at the end, you end up with the Hodge diamond or with the middle cohomology of this Picard curve, which has a 3-1 and 3-1-0 and 3-0-1 periods. So you can actually understand that these two variations of hot structures are equivalent. So let me come to the application to QFT. So you might wonder why I consider this graph. So I can consider this graph again. So it turns out that in a way that I hope you understand, that this graph is actually not irrelevant because it has a funny topology. It actually does appear in as simple the three-loop version of it appears in a simple problem as calculating the self-energy of the photon in 3 loops. So then these periods actually appear. That would be periods of a K3. So how is this? So first of all, one has to see that, that this graph here leads to this complete intersection Calabi-Yau, but this is not for all graphs that you can look at. So if you take another graph, there will be not a single Calabi-Yau associated to this graph. So in this case, for instance, this is called the ice cone graph. There is not a single Calabi-Yau that gives you the maximal cut or whatever. Actually, you cannot do a maximal cut, which has to do with this fact, whose periods are directly related to physical properties of this graph. So rather what the people do is, so how they obtain in the Feynman graph community this analog of the Gauss-Manin connection is as follows. So they take this graph and they write propagators for all the propagators they see in the graph. And they take arbitrary exponential to all these propagators. And they do, of course, all these propagators contain K because they, or let's say the internal momentum they contain. I should have called this K. And then this is the graph. And they write this itergo. And of course, and they're also not specific about what is the dimension of this graph, so this can be also kept arbitrary at this moment. And then, as I said before, they do a couple of Lorentz invariant quantities for the external x. So, for instance, products of the momentum, mass squares, and so on. And then they decide on how many ratios of these set I this depends. And this will be the moduli of my problem. And then they do this exponential of the propagators and actually also this dimension in a lattice. So these are the exponents of the propagator. They do this in a lattice. And they consider such the master integrals where this lattice is fixed. And they look like this. And then they have a very simple exact form that they can build from this master integrals, and that is this one. So the thing is, this one is exact, so then you get 0. And you can do now partial integration. And this partial integration is exactly the thing that Griffiths does if he does the reduction method to derive the Picard-Fuchs equation. So it's actually the analog of that. And there are some deep theorems. So for instance, there is a finite region in the lattice that contains all the non-vanishing master integrals. And then you can, in this basis of master integral, you can express the derivative with respect to the set K as linear combinations with rational coefficients by these IPP relations. So you get something like the Gauss-Manin connection from that. And of course, the master integrals are sort of, or the integrants of the master integrals are sort of what they call the graph cohomology. So it's the cohomology of the graph, and it's basically the cohomology of a Calabi-Yau for these banana graph, but in general it's more complicated. So this is, so to say, the dictionary. So the integration by parts. This corresponds. The IPP is called stands for integration by parts relations. This corresponds to the Griffiths reduction method, and then a complete set of IPP relations. This corresponds to the complete Picard-Fuchs ideal in the case of this banana graph. So that is very powerful. But as I said, there is, so to say, a finite region in the lattice that all your integrals, master integrals, are in. And then you take this master integrals and you write your differential equation like that, where this is the connection matrix of the Gauss-Manin. And now you see the epsilon is still in, because I also had this also depend on epsilon because the dimension is arbitrary. And now you need a better basis in order to extract it in order for epsilon. And you do this by rotating the master integral and the connection. So this is a complicated step, but you can get better and better. And the best one is if the connection, and I don't think there's a theorem that this is achievable, but in many examples you can just achieve it. So then has this form, and now you see what happens here very nicely. So for instance, you see here a block, and this block acts on this period, and this block is in general a period integral of a Gauss-Manin connection of a Calabi-Yau. But then there are, so to say, subgraphs where some of this exponential were 0. These are subgraphs. And you see these also occur, and then they appear in the connection. So for instance, for these periods, this line, or this couple of lines give an inhomogeneous differential equation. So the inhomogeneities appear in this approach as the subgraphs of the graph that you are considering. And that is also the reason that the banana graph is so nice and simple, because if you cut any of these propagators, then it becomes a tadpole. And there is no momentum integral to be done, because it's just fixed by the momentum conservation. So that's why the reason that this is so easy. But on the other hand, you can say that the banana graph appears in any of the other graphs that you wish to consider of any topology. And that's the reason that, for instance, in the self-energy of the photon, you get these Calabi-Yau periods if you try to solve them. So this is very nice. So in this case here, you see that these blocks that I indicate that you can read off if you achieve this epsilon form with the diagonalization are Gauss-Manin connections of Calabi-Yaus, and also from the ice cone graph is actually pretty much the right blocks, because these two blocks are the banana graph at Z and the banana graph at 1 over Z. So it's somehow clear that the banana graph is in this ice cone graph in this way. So let me summarize what I said in the second part, because I come shortly to the last part. So, well, anyway, the maximal cut integrals, they correspond often to these periods of Calabi-Yau. Then the dimensional ratios are the unobstructed moduli of the Calabi-Yau. The integration by parts relation is kind of like the Griffiths reduction, which also explains why these Calabi-Yau motifs come up over and over again. And then the integral of the master, the integral basis of the master integral is basically the middle cohomology, and then the complete set of differential equation you get in this form by putting them, so to say, considering the subgraphs as the inhomogeneous pieces. So that is the next example, and that, so to say, shows that Calabi-Yau's periods and their iterated integrals will appear really in calculations that you have to do for the LHC, because or for that matter, to calculate the magnetic moment of the electron or something like that. So it's really like that. And another application is this word line approach to, I mean, it's a quantum field theory approach to a classical problem in scattering of black holes. So it's a little stupid, in fact, if you think about it, that you solve this by a quantum gravity formalism, but it works and is the only formalism that gives results. So basically the problem is you scatter two black holes, and don't think about supersymmetric black holes, just ordinary black holes, and you want to know let's say the one, what is the gravitational waves that's emitted in this process, and what is, so to say, the impact parameter doing? I mean, what is the scattering angle at the end of the day? So what you do is a kind of a wordsheet, a word line approach. You write down this action, and you perturb this action a little bit from the flat space. In particular, you perturb the metric from the flat space. And then you calculate from the initial data, in particular this impact parameter, you want to calculate how the momentum changes. And you get for this momentum change something that is expandable in the weak gravitational coupling, and an expression that you can calculate in this Swinger-Keldysh formalism by a Feynman graph expansion. And the upshot is that if you do this now in the 4 PM approximation, then it's g to the 4. It is, so it's a certain degree in the gravitational coupling. Then you look at these Feynman graphs, and what you see is there's a Feynman graph of a K3. Very nice. So and it, so to say, happens that this is a Feynman graph of a K3, since any K3 factorizes one parameter K3. Remember, there's only one parameter in this problem, but any period of a K3 is actually a symmetric product of elliptic curves. And therefore, people have not, so to say, seen. They thought it was elliptic curves, but in fact, it's a K3. And then we looked in the 5 PM approximation, and we're hoping to find Calabi-Yau threefolds. And indeed, I mean, you see, if you look at this graph now, this graph, so then you find, I mean, you do, basically the formalism is very much like by this IPP relations. So we found, so to say, the Gauss-Manin connection, and the Gauss-Manin connection of that was the Gauss-Manin connection of 4 quadrics in in P7, and then we looked at further Calabi-Yau that appear. So we found there's a further Calabi-Yau, which was found by a different group, but there's also a very interesting, finally there's exactly the K3 that whose Picard-Fuchs equation a priori used to prove the irrationality of zeta 3. So there come very funny Calabi-Yaus in this problem. And I have not a good overview of what kind of what kind of complexities is in this Calabi-Yau that you find in these calculations, but I can say that that the basically in every problem of this perturbative problem in quantum field theory, or its application here to gravitational scattering, you find period motives of Calabi-Yau. And if you want to express if you want to get the answer in terms of transcendental functions, you have to take, this will be Calabi-Yau periods plus iterated integrals of Calabi-Yau periods. So it's a very well-defined class of transcendental function, which seems to quite generally govern these problems in quantum field theory and also in this gravitational problem. So maybe I should end then. And so the conclusion is sort of, okay, I mean, these Calabi-Yau periods, they appeared in physics in the Kepler problem very early. And sort of physics and mathematics has developed, of course, and on the way we have seen all kinds of amazing things about these Calabi-Yau periods. I mean, in particular in respect with enumerative geometry that come from string theory, but I also have seen things in arithmetic geometry on this Calabi-Yau periods. And also in this respect, you can say that the Calabi-Yau periods are the natural, so to say, next generation of elliptic curves. I mean, because they also have modularities in their Hasselbalch zeta function, etc., etc. And so it leads more and more up, and these periods still play a role for a reason that, that is, I can explain formally, but what is the deep reason, I don't know. So now they solve problems like particle physics or scattering of black holes. Okay, thank you.
Thank you very much. We have plenty of time for questions. Kumrun?
Thanks for an interesting talk. So you're relating particular loops to particular dimension Calabi-Yau.
Yes.
You generally get compact Calabi-Yau?
Yes.
The fact
the
that
master example is just this one.
Yes. The fact that the Calabi-Yau are believed to be finite in number, even though you're getting a particular regions of moduli space of complex structure of them, the fact that there are a finite number of Calabi-Yau, what does it translate to in terms of complexity of the loops? Are there relation to their finite number of good quantum field theories? Because at each loop there's only finite number of Calabi-Yau, and if so, can you have a bound on the number of Calabi-Yau by studying that question? What is the relation with finiteness?
I mean, I could imagine that for a given quantum field theory and doing this particular reduction to the subgraphs and so on, since there is not an arbitrary complication in the topology of these graphs, because it's just given by the standard model, that then the Calabi-Yaus will be finite. And I suspect actually they are very lame in a sense. Not many types of Calabi-Yau. So I was already happy that in this gravitational problem, I found a Calabi-Yau like this one that was considered by Boykers for this upper E problem. That's more complicated. But this Calabi-Yau is the simplest one that Candelas would have written down. And it appears over and over and over. So I think if you ask the question very general, let's say for a renormalizable quantum field theory, maybe you can point to a class of Calabi-Yaus, but it's of course a very complicated question.
So you don't expect to get all?
I don't expect to get all.
I see. And is there anything connected in these, at least in these simple examples, to things other than periods, or it's just the periods that arise?
No, as I said, I mean, what appears more typically is the relative periods that we calculate.
No, I know, but basically integrals over some chains or something. Are there anything, like for example, in the topological string, we have these higher loop quantum amplitudes. Are there anything more fancy?
Good question. I mean, I believe, if you think about the topological string, how we solve it today, we don't solve it by Feynman graphs. I think you were very proud to solve it by Feynman graphs. But today, we solve it by its symmetries. And this is more in the spirit of these master integrals. We combined blocks of certain modular structures because we understand that these blocks have to have certain symmetries. And in this sense, it becomes, instead of a G factorial growth, it becomes a polynomial growth. The way that we solve the topological string. And actually, it's very interesting. In a sense, you can also say in the topological string, if you look at the propagator of the quintic is actually the Calabi-Yau of a period of a fourfold. So it's if these terms that you get are also belonging to higher dimensional Calabi-Yau in the topological string. So it's actually a good analogy in this sense.
Okay, any other questions? Yes, in the back over there.
Thanks for the very nice talk. That last family of K3 surfaces that you had is naturally written as an elliptic fibration. I'm wondering if you've seen other fibration structures on the Calabi-Yaus that you've written down, and if those fibration structures tell you anything about relationships between the amplitudes.
Yeah, that's a good question, but I can say it's almost trivial. So remember, this is a complete intersection, and for instance, the elliptic curve would be just take P1, 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 and take 1, 1, 1. So this is the elliptic curve version of this thing, and it actually corresponds to the sunset graph. Now what you do is you can, for instance, view any of these parameters also as the base. And if you take the mass to 0, then you get a decompactification limit. And of course, you can do this in all ways. So it's a vibration with respect to all of these bases. So it's an elliptic multivibration, or let's say, then you also have K3 over P1 and Calabi-Yau threefold over P1 and so on. So of course it's reflected in a very trivial sense in this combinatoric of this graph. And of course, one thing which is not to be underestimated is the following fact. If you know what the geometry is, then you have from string theory the gamma class or gamma head class formalism. So it's no problem to write immediately down an integral symplectic basis and identify what the period is. And that's very powerful. The people in the Feynman graph community didn't know that, what to write down. And in this sense, it's a real contribution to what they are doing.
Thank you.
Okay, one question here, please.
So I wanted to ask if you also tried with toric hypersurface Calabi-Yaus or only for CCs. So I'm asking this because these del Pezzo surfaces, they are very common divisors of toric hypersurface Calabi-Yaus, but they don't appear in CCs very often. So do you think that there could be a link to these these?
Yeah, I mean the thing is, for instance, you can write this problem also as toric hypersurface, and for this graph, the toric polyhedron would look like this. And you see this is fine because you have 3 automorphisms, so you can identify this with M1, M2, M3. But if you do the same thing not in 2 dimension, but in 4 dimension, your toric polyhedron will have something like 18 variables. So it turns out that the physical problem is a very small subslice in this problem. And that's why we thought, okay, let's write down a Calabi-Yau where it's not a subslice, but where it's naturally identified as moduli space. And you can actually, in these higher dimensional problems, you can single out the subslice by doing a transition on the Calabi-Yau to this Calabi-Yau. So basically, you realize that at this point, at the physical moduli space, the Calabi-Yau is singular, you blow it up, and then you get this Calabi-Yau. So, as I said, you should not worry about how it's realized. You should not even worry it. Maybe, I don't know whether this is whether we are right for this perspective. You should maybe view it as a Riemann-Hilbert problem. You give the monodromies and so on, or you view it as a problem in Galois theory. But you can find the same motive and that's why I stress the motive word. You can find the same motive in many geometrical realizations. And of course, for the Feynman graphs, you don't care, because as long as it gives you the answer, you don't care so much about it. So yeah, whether you realize it first as a hypersurface in a toric variety or immediately like that, the calculation is just simpler in this way.
Yeah, actually, my interest was like, because these CCs have very, very less number of, for example, say distinct divisor topologies. For example, when we classified all these 8,000 CCs examples, then we find that there are only 11 which appears as a divisor of the coordinate divisor topology. But for hypersurface in toric varieties, we have much more structure. So I was wondering whether when you go beyond CCs and start using toric hypersurfaces, then we have much more to play with, and maybe we could classify based on K3 fibration or say elliptic fibration and things like that. So I'm not sure. Maybe it is too early for this approach to.
As far as the application to Feynman graph goes, we learned something about Calabi-Yau, but the Calabi-Yau that do appear are relatively easy, I have to admit. I mean, this one that gives the irrationality of zeta 3 is more or less the highlight.
Any further question? Okay, don't see any, so let's thank again Albrecht for the inspiring talk. So we take 3 minutes break before the contributed talk session. Banu Kiran? Yeah. Okay, great. Actually, you know, are the slides already uploaded?
Yes. Well, actually, it's, since there are many, it's better to use this one, so we don't have to exchange the microphone as we. Fine. Yes, well, fine. Puoi trovare?
Sì, qui guarda.
Ah, ok.
Ora, come si mette a scrivere?
Fuori? So we'll use these two microphones. And, okay, forward and backward. If you keep it pressed, there is a...
Okay, so let's resume. Please be seated. Okay, so today we start with the Banu Kiran Sandipudi from ICTS telling us about the formations of monoidal categories.
I thank the organizers for this opportunity to speak here today. I'm going to talk about deformations of monoidal categories, and this is part of a project that I've been working on with my advisor Pranav Pandit. To begin with, I'll recall some aspects of deformation theory which will be useful for us. If K is a field of characteristic 0 and G is a DG Lie algebra over K, then a Murakarta element in G is defined to be a solution to the equation you see on the screen. It is known that deformations of objects living over K are associated to Murakarta elements in DG Lie algebras over K. Let me illustrate this in an example of A-infinity algebras. So an A-infinity algebra is the data of a graded vector space V, vector space V along with a bunch of maps Mn's from V tensor n to V of degree 2 minus n, such that these bunch of equations are satisfied, which basically encode the homotopy coherent associativity of the multiplication. Now in case M0 is not 0, so notice that here I said n is greater than or equal to 1, but if we take n to be going from 0 onwards, then the M0 term is called the curvature, and such algebras where M0 is non-zero are called curved infinity algebras. So these are not so nice objects, meaning there's no good notion of a quasi-isomorphism of curved infinity algebras. And there are certain caveats involved in defining a non-trivial theory of such algebras. So for these reasons, we would like to restrict ourselves to uncurved infinity algebras, meaning M0 term we assume to be 0. Now a deformation of this structure is a perturbation of the multiplications. So a first order deformation is a first order perturbation Mn prime of Mn. So Mn prime is Mn plus eta n times t, where t square is 0 because we are looking at first order perturbations. And we impose the infinity relations on Mn prime and conclude that eta is a Murakarta element in the shifted Hochschild complex of V. So this is the association between deformations and Murakarta elements. The problem comes from this observation that Murakarta elements may induce curvature, meaning even if we start with an uncurved infinity algebra, meaning M0 is 0, one cannot always guarantee that Mn0, M prime 0 is also 0 all the time. So for this reason, we say that deformations are not the same as Murakarta elements. So there's an obstruction to describing deformations in terms of Murakarta elements, which is basically the presence of this curvature. So that will be kind of the main point of the talk. That's what we want to address. Let me reinterpret Murakata elements in a different way, which will be useful for us later on. So if A is an augmented commutative DG algebra and MA is the augmentation ideals.
Is this happening because you decided not to include n equal to 0 in the, or n equal to -1 in the Rothschild cohomology?
Yeah.
In the previous slide, sorry.
Yeah, there's no m equal to previous slide. Yeah, we don't have m equal to -1.
So here there is an m equal to 0 term too, right?
Yeah, we don't want m equal to 0. That gives us curved infinity algebras, and we don't want to.
Absolutely, but
yeah.
Why do you say doesn't the Murakata equation includes the fact that there is no curvature?
So deformations for us don't have curvature. We want to stay with uncurved objects. So deformations are defined to not be curved.
I think that Murakata. So I'm saying in the shift to homology complex, do you include the m equal to 0 part?
Yeah, that is a full complex. So a priori it will have m0 terms.
So wouldn't the Murakata equation imply that there is no curvature?
No. I don't think
Maybe we can keep this for after the talk and then move on since we have very limited time. So.
Let me continue. Yeah, so A is an augmented commutative DG algebra and MA is the augmentation ideal, meaning it's in the kernel of the map from A to K. G is a DG Lie algebra and C star G is the Chevalier-Allenberg complex. This is the complex which computes the Lie algebra cohomology of G. Then Murakata elements in G tensor MA are the same as maps of augmented commutative DG algebras from C star G to A, which by adjunction is the same as maps of DG Lie algebras from DA to G, where DA is the commutative Koszul dual of A. It's the relative tangent complex of A. Right. So let me focus on the objects of interest, which are monoidal categories. So in the context of topological field theory, line operators and point operators in TFTs form a category, and fusion of line operators gives us a monoidal structure on these categories. So the first diagram shows composition, which is the fusion of point operators along the lines, and then tensor structures coming from fusing line operators, and the compatibility is giving us the functoriality of the monoidal structure. In higher theories, so these diagrams are drawn in 2 dimensions, but in theories of higher dimensions, we can take these line operators around each other and then fuse them. That gives us a braided monoidal structure, or more generally an EN monoidal structure. So this kind of nudges us to go to the world of non-commutative geometry to study this problem, and that's what we do. So we go to the world of non-commutative geometry, where we replace commutative DG algebras with EN algebras and Murakata elements. So these are now known to us to be Murakata elements. So these are replaced by certain generalizations of Murakata elements. Let me say what that generalization is in the context of this talk. So if C is a monoidal K-linear category, one can talk about the monoidal center of C. It's the endomorphism object. It comes from looking at endomorphisms of C viewed as a bimodule over itself. So, and then we have this object here, which is the generalization of the Murakata elements. And D3 is the E3 Koszul dual, a generalization of the commutative Koszul dual. So let me say what this generalization is. So a map from D3A into the center of C, Z of C, is the same as an action of D3A on C, because the center of C is the endomorphism object, and giving a map into the endomorphism object is the same as giving an action. And this formula computes the E3 Koszul dual. So as a broad principle, we say that a deformation of an object induces a realization of a generalized symmetry of that object based on this argument. So the setup, if C is a monoidal K-linear category, we define def C to be the space of deformations of C, act C to be the space of Koszul dual actions, which is given by the formula we saw in the previous slide. And we construct a functor, goes from def C to act C. So appealing to the example of infinity algebras, def C is thought of as the space of m primes, act C is thought of as space of etas, and theta will take an m prime and associate to it the corresponding eta. And this map is in general not an equivalence. But over formal power series, if we only consider formal deformations, and we take C to be the equivalent to the category of modules over an E2 algebra, such that the E2 algebra is homologically bounded below, that is this condition, then one can show that deformations of C are equivalent to these actions of the causal dual of the former power series. We can rephrase it by saying Murakatta elements are equivalent to deformations of C over the formal power series. We say the curvature is gauged away. This is an extension of a similar result by Blanc, Azarkov, and Pandit for K-linear categories and Loewen, Vandenberg for A infinity categories. So in conclusion, just to summarize, if C is a K-linear, monoidal K-linear category, Murakatta elements correspond to curved deformations in general. But if C satisfies a suitable hypothesis, then formal deformations of C are equivalent to Murakatta elements.
Thank you. Questions or comments? Yes, please. Yeah.
Often, if you have a deformation problem, then the fact that somehow all deformations are good, it has to do with the vanishing of some obstruction somewhere. And so can you phrase this condition, so you had some hypothesis under which all deformations somehow were good.
Right.
Can you phrase that hypothesis in terms of some place where an obstruction lives and the vanishing of that obstruction?
So here there was a compact generator. The C was viewed as a module category over some E2 algebra. And in the obstruction would be to the obstruction of this compact generator to deform along with the category. And if that obstruction vanishes, the generator deforms, and then we say the category also deforms with it. But yeah, so this hypothesis kind of guarantees that the generator always deforms.
Okay, I think we need to move on. So let's thank the speaker again. Okay, so we now have Johanna Koman from KIPMU telling us about the VOAs from topology, number theory, and SQFTs.
Thank you very much for the introduction, and thank you to the organizers for giving me the opportunity to speak today. So, as Boris said, what I want to tell you today...
Closer to the mic.
all right, thank you. Thank you to the organizers for the opportunity to talk today. As Boris mentioned, what I want to discuss are some new results concerning vertex operator algebras, but coming from the perspective of three-dimensional topology, number theory, and 3D SQFTs. Now, a motivation here comes from the ubiquity of VOAs, which appear as related algebraic structures in each of these three contexts. The VOAs, they formalize mathematically the idea of having operators inserted at points on a Riemann surface and which get multiplied via operator product expansions where they are collided. So in this way, they describe, for example, the chiral half of two-dimensional conformal field theories, the underlying algebraic structure. Now, in terms of their definition, they were introduced already in the mid-1980s, and the definition involves a set of defining data which contains a vector space and a set of axioms that this data satisfies. And with vertex operator algebras having been around now for almost 40 years, and with research related to them evolving for such a long time, by now there exist numerous connections to other areas of mathematics, notably geometry, topology, and as mentioned in the title, number theory. Now, connections to supersymmetric quantum field theories, these emerge from various correspondences, whether they are 2D, 3D, 2D, 4D, where the VOAs and their modules or representation categories appear as meaningful invariants for the quantum field theories in higher dimensions. For instance, the VOAs can appear embedded into the physical space of the higher dimensional QFT, where they capture distinguished algebras of local operators on some surface. And now here, canonical examples when one discusses VOAs are the affine vertex operator algebras associated to a simple Lie algebra and an invariant bilinear form, and which are strongly and freely generated by a set of fields which correspond to the elements in a basis of the underlying Lie algebra that one started with. And from these affine VOAs, other examples can be constructed, defined by certain standard procedures, such as constructing extensions or taking cohomologies. So for instance, affine W algebras, these can be defined for simple Lie algebra G and a nilpotent element in this Lie algebra from the cohomology with respect to a certain corresponding nilpotent operator on a complex which is constructed from the universal affine vertex operator algebra and a corresponding fermionic ghost counterpart. And then secondly, the example of logarithmic W algebras, which have been defined as the intersection kernel of certain screening operators on a lattice VOA, so they are defined by restrictions from lattice vertex operator algebras, and they have been shown to be extensions of the affine W algebras that I just mentioned. Now what I would like you to take away from these 10 minutes as the punchline is how such algebraic structures have appeared recently in two particular contexts in relation to 3D topology and 3D supersymmetric quantum field theories, and what are some of the implications here. Now the first case that I want to discuss, here the vertex operator algebras, they appear inside a wider network of relations that connect from a physical point of view, a certain type of 3D, 2D coupled systems, so these are three-dimensional n equal to 2 supersymmetric quantum field theories with a boundary, which are related via 3D correspondence to some auxiliary three-dimensional manifolds. They are related to vertex operator algebras, and then there is another box that says number theory, and this is because one of the objects that gets identified in each of these three contexts are a certain type of Q series. So these are formal power series expansions in parameter Q, which have intriguing number theory properties and which have different interpretations depending on the context where one discusses them. From the physical point of view, they represent a half index, but from the point of view of the auxiliary tree manifold, they are topological invariant. And these get identified with characters of a logarithmic vertex operator algebra. So here the easiest point to start with is from 3D topology, because these invariants, they are defined for a certain class of three-dimensional manifolds, which can be constructed by dense surgery on framed connected links inside of a tree sphere, where the surgery data is equivalently captured by a planar graph that has decorations. And then the invariants were specified in terms of this surgery data, the choice of a Lie algebra, and potentially also including line defects on the links inside of the tree sphere. The invariants were specified by a contour integral. Now, this provides a precise algorithm for computing these invariants with the caveat that it has a restriction on the type of manifolds for which it is applicable. And this is in order for the Q series that are generated to be convergent inside of the unit disk. But now, assuming that this constraint is satisfied, for a certain type of manifolds, these invariants have been shown to be in the span of linear combinations of false data functions. And the false data functions, they have index, which is only determined by the data of the tree manifold. Now, the caveat that I mentioned is very important because changing the orientation of the manifold poses a problem because it leads to divergent Q series. And formally, this is equivalent to changing the sign of the parameter tau going to the other side. So this gives rise to the subtle problem of finding these invariants on the other side, and various approaches have been attempted in literature. And now the proposal that I have developed with my collaborators relies crucially on the quantum modular structure of these invariants. And there are three key steps here. The first is proving the precise quantum modular structure of the invariants, which are vector-valued quantum modular forms. And then the requirement for going to the other side is precisely that pairs of invariants should have compatible modular structures as they approach the rational line. And in this way, we were able to define the Mock defect invariants as regularized indefinite data functions, where the crucial point is to determine the regularization data. And from this, we were able to construct the corresponding VOAs. Now, case 2, you heard about yesterday in Masahito's talk.
But you had to learn another minute if you want to spend a minute.
Well,
there was 1 minute left.
Oh, perfect. All right. Well, then, in that case 2, what the punchline is that in case 1, the identification of these vertex operator algebras, it was technically complicated, but it still relied only on functions, on Q series. More fundamental relation would be at the level of the underlying vector spaces. And this is what we heard about yesterday morning in Masahito's talk, because in the case, notably, of three-dimensional n equal to 4 non-abelian quiver gauge theories, a topological twist allows to identify a vertex operator algebra on the boundary by curlizing an underlying classical geometry. So here, by looking at sheaves of H-periodic vertex operator algebras, the global sections define the VOAs concretely, and this opens the door to many exciting generalizations, drawing parallels between the two cases.
Thank you very much, and sorry for cutting a little bit too early.
Perhaps you said already, and I missed it, but what class of 3 manifolds do you consider?
In which case? Case 1 or case 2?
I better not answer that. Tell me what classes of 3 manifolds you consider.
In case 1, the story is a bit intricate. It's a little bit, in case 1, the story is a bit intricate because from the physical point of view, the background of the physical theories is just the cigar background. Then from the point of view of 3D topology, the auxiliary manifolds, the ones that we considered are certain cipher fibrations over the tree sphere. But they have a plumbing description in general. So that's case 1. And in case 1, the easier point to start with is from 3D topology, because there the corresponding supersymmetric quantum field theories in general are not known to have a Lagrangian description. So it's easier to start from quantum invariance, and hence, yes, these quantum modular forms. In case 2, the background, the three-dimensional manifold considered, is really the physical space-time background. And in general, that should just have a transverse soromorphic foliation. For us, we only considered effectively a complex surface with a half-line.
So could you consider a general 3-manifold fibered over a circle, which your notation suggested, I thought?
In which of the two cases?
I'm not going to answer that. Do you have any case where that's the class of manifolds you consider?
Yes, in case 1, that is exactly one of the types of manifolds that can be considered.
Vibration over a circle?
Well, circle vibrations.
No,
yes.
I'm asking the opposite. A vibration over a circle.
I need to think about it.
Thank you. In view of time, I think we have to move on. So let's thank again Joanna. Great talk.
This one? This one, you have the point. Microphone. Good.
Okay, so now we have Sebyok Jeon from CERN telling us about mirror operators and membrane intersections.
First of all, I would like to thank the organizers for the chance to speak. This is about a comic paper with Nathan Housey in a work in progress. I'll explain why mirror operators and R metrics. So let me recap the mirror transformations for W algebra. So the mirror operator is this former differential operators combined with affine G1 current. So to get the generating currents of the W algebra, you take the products of them and copies of them and just consecutive products of them. So it should remind you that product of R matrix is under some coproduct operations, assuming there's an underlying quantum algebra. And there's another clue, the Maury-Okunkov R matrix. So the previous mirror transformations shouldn't depend on the ordering of any of the two mirror operators. And what does the job is this relation. So there's a what's called Maury-Okunkov R matrix that intertwines two different orderings of the mirror operators. So once I write down this mirror operator as R1 and R2, you can see that this really looks like a kind of Yang-Baxter equation. But for that, our mirror operator has to be an R matrix. So I will answer this question in some sort of version. So I will not exactly the answer that the problem about the problem that I posed, but answer to the Q deformation of the problem, because there's a reason why I prefer this. And there's an underlying twisted M theory background, and in this background, this Q deformation amounts to change some holomorphic surfaces to C star cross C star. So for the cases of C cross C and C cross C star, there's many other works, and of course I borrowed a lot of intuitions from these works. So what's the twisted M theory? It's an M theory defined on this 11-dimensional background. It's topological along this 7-dimensional world volume and holomorphic along these two holomorphic surfaces. I said it's C star cross C star. There's an omega deformation that I didn't explain in very detail, but it amounts to turning of potentials along with respect to the rotations of these output planes. So effectively, the theory localizes onto this 5-dimensional wall volume. It's called 5D transiments theory. So we can put some M branes onto this M theory, and there are M2 and M5 branes. M2 branes can wrap this R2, one of the R2 planes and wrap R, and M5 branes can wrap two R2 planes and a holomorphic curve. Never mind about these PQ choices. I'll only focus on the 1, 0. So namely, C1, 0 is a C star X plane. So these, I show some possibilities of the M2 and M5 branes, and as you can see, in the 5D transiments theory, they engineer line defects or surface defects. So they have to consistently couple to the 5D gauge theory, and the gauge invariance of the coupling requires the algebra of local operators on these defects to be representations of some quantum algebra. The suggestion is that for our case of C star cross C star, it's a quantum toroidal algebra. So in principle, I have to give you the definition of this quantum toroidal algebra by giving you the generating currents and the relations. Let me not do that, but let me just deliver the notion that it's a certain Q1 deformation of what's called quantum torus algebra. It's simple algebra generated by X and Z with this relation. And as you can see, Q1 and Q2 enter in asymmetric way, but this full quantum toroidal algebra has triality of exchanging at Q1, Q2, and also Q3, which is Q1 inverse, Q2 inverse. So for the M2 brane, we assign, what the algebra that's assigned is the quantum torus algebra itself. So I express the same algebra, but now I explicitly write down this difference operator. I didn't tell you, but E, F, H's are the generating modes of this quantum toroidal algebra, and they are mapped to the quantum torus algebra in this way. C and C perp are the center elements. For the single M5 brane, we associate a free boson. So the free boson is generated by these AR modes with these commutation relations. EF, K currents, generating currents are mapped to certain vertex operators. So now what we can do is stacking up these defects. So here I'm visualizing certain fusion of the line defects. So let's imagine you have two parallel line defects, two line defects. Then they can be fused into a single line defect. So it means that the local operators of the fused line defect can be built out of the local operators of these individual line defects. And algebraically, this quantum toroidal algebra is a co-algebra. So there's an operation that preserves the algebra structure, and you can represent on respective representations associated to this line defects to get the new representation associated to the fused line defect. So let me just mention that. So I started with a single M2 brane. You can stack them up, the parallel one. What you get is what's called the spherical double Van Hecke algebra. For the non-parallel case, this is a new representation, and I call it generalized Lucena-Schneider representation because if I have only one set of X prime and X double prime, it will really become what's called the Lucena-Schneider representation of quantum toroidal algebra. We can also play the same game for the surface defects. So on the surface defect, there are free bosons, and you can stack them up to from new algebras. So this case will be what's called the Q-deformed W algebra. And if I allow the most generic orientation, it will be what's called the Q-deformed Y algebra, which Davide Gaiotto and Miroslav Babchak studied. So now what's the mirror operator? So for the mirror operator, I consider the intersection between the M5 and M2. So it's the single M2 and single M5. At the intersection point, there's this red dot. There's a there's a local operator supported, and I call it R. So it has to be gauge, it has to be gauge invariant, and classically the gauge invariant condition can be figured out by drawing a small sphere, and the gauge variation comes from its intersections with the defects. So there's a north pole, a south pole, and also there's a contour on the surface. So there's an ordering on the increasing R direction. So the south pole contribution acts from the right, the north pole contribution acts from the left. And you might think there's a single contribution from the surface defect, but it's important that the red dot is not the origin. So when you do the mod expansion, you can decompose this contour into the two independent contours that goes around this zero. So you really have two contributions from the inward and the outward. So that's a gauge invariance condition in the classical level. It has to uplift to include the nonlinear contributions at the quantum level, and then we postulate to involve this coproduct too. This relation doesn't come out of nowhere. We know there's a notion of universal R matrix, and it can be exactly solved to lead to this R matrix intertwining M2 and M5 representation. And by stack this M5 brane up, the R matrix between on the right picture should be decomposed into products of this individual R matrices. That's the usual thing in the coproduct operations. We can also exactly figure out which screening charges they are commute with by using the M2 branes ending on the M5 branes, which I didn't have too much time to talk. There's also a relation with QQ characters, 3D half indices, and also there's a direct computations that you can do in the perturbation theory of the 5D Chern-Simons theory. That's it. Thank you.
We have time for a couple of questions.
Do you have some impression what's happened on the Poisson level and on the classical level?
Sorry, I
didn't. Quasi-classical level. Your picture.
Quasi-classical level meaning the.
I mean these Muir operators.
So you want the Muir operators for the W algebra, not the
all your Q's go to what's happening.
Yeah. So just take the limit of that this is called degeneration limit. Just take the limit to this expression. We recover that differential operators instead of difference operator. So at the bottom line, you see this Muir operator expanded in powers of difference operator, but that difference operator turns out to be differential operator in this limit. So you're going to recover it. Sorry, let me just mention one thing. So for the case of C equals 3, you see this factor in the parentheses can vanish. That's very important. So that only first two terms in the infinite summation can contribute in that case. That's why Muir operator is very simple.
Okay, thank you. I hope we can discuss later.
Another question? Okay, I don't see any, so let's thank Sebiok for the nice talk. Next speaker is Élise Lepage from Berkeley.
Okay.
Pointer?
Yeah.
These are the microphones.
Okay. Okay. Hi. Oh, yeah. Oh, thank you for the opportunity to speak. I'm going to be talking about computations of homological link invariance from categories of A-branes. So this is largely going to build on Mina's talk from yesterday, but I'm going to hopefully convey how we can explicitly calculate the link homology that Mina introduced yesterday, and I'm going to give a sketch of how we prove the invariance. So this is based on joint work with Mina and Miroslav Rabchak, and work to appear with Mina and Ivan Danilenko. So just to briefly review how we get the knot invariance that we want to calculate is they're going to come from A-branes. So eventually we're going to choose a certain configuration of A-branes, and knot invariance are going to come from HOMs from one A-brane to another A-brane. And so in the specific A model we want to consider, the target space is going to be based on a choice of a Lie algebra. So it's going to be some number of symmetric products of an infinite cylinder, where the number of symmetric products we have comes from the number of roots of the Lie algebra. So we can think of this as the configuration space of colored points in an infinite cylinder, where each color corresponds to a different root of the Lie algebra. And we're also going to add a potential. And so the role of the potential is just going to be that it equips the A-branes with a grading. So the resulting homology theory is going to have two gradings. It's going to have a homological grading, and it's going to have an additional grading coming from the potential that we call the equivariant grading. And so, for example, the potential is going to get, well, the grading is going to get contributions from monodromies around certain marked points. These are the points I drew as x's. So these points are going to be labeled by weights of G, or equivalently, we could say that they're labeled by highest weight representations of G. And so then, in order to build knot invariants, we want to choose special A-branes, which I'll refer to as cups and caps, which you can imagine as like the top and bottom of braids. And so the way we do this is we want to choose a specific representation to color our knot. And so the cups and caps are going to categorify conformal blocks that represent this representation V and its dual representation fusing to the trivial representation. And so the way we do this is we choose a puncture labeled by highest weight representation V and its dual representation, and then we're going to choose an A-brane that fuses these two punctures together. And so we have to make certain choices of these parameters dA that depend on the representation we choose. So here I have a couple examples of what these look like for the case of SU4. And so I've drawn a Dinkin diagram on the far right to give you an idea of I want each root to correspond to a different color. So I can see here I have 3 roots. I've drawn them each as a different color. And so in the top picture, I have a representation with highest weight W1. It's going to be dual to the representation with highest weight W3. So it's the blue puncture and the green puncture fusing together to the identity. And then I choose the A-brane is going to be the product of these 3 one-dimensional surfaces. So this figure 8 brane I've drawn in the top picture, I guess I can use the pointer. This figure 8 brane is going to be on the product of 3 cylinders is where it's living. And so I would say that this refers to the cup brane, and then this straight line brane refers to the cap brane. And so what these 3 dots represent is just these 3 dots can be coordinates anywhere along this straight line with the restriction that the green dot is always on the same side of the orange dot, and the orange dot's always on the same side of the blue dots. So the dots can't switch order. Then I have another example for this other rep of SU4 that's actually self-dual. So it's like the 2 orange punctures fusing together. And so then we actually want to build knots out of these cups and caps. And so the way we do this is from a presentation of a link as a braid closure. So I have an example shown here for the Hoff link. And so you can see the way I have my link presented, it starts with a pair of cups at the bottom. So here I would say this is 2 cups. And then I braid the 2 middle strands. So it's like I'm braiding the 2 cups, and then I have the caps above this dashed line. And so heuristically, as A-branes, I want to say the part above the dashed line corresponds to 2 sort of intervals, and then I have another pair of intervals for the part below the dashed line, and then I braid them. So I can see in my braid, I exchange the 2 middle strands twice. And so that corresponds to I exchange the 2 punctures twice. And so then I want to translate this heuristic picture to actual A-branes, like I had on the previous slide. So here's some examples. This is for the fundamental rep of SU2, and for one of the SU4 reps I showed you. And so in order to get link homology, what I want to do is I want to take the space of Homs between the top brane and the bottom brane. So what you would actually do is they would be living in the same space. So you would overlay them, and you would count their intersection points. These would be some perturbative ground states. And then you would want to calculate some corrections coming from holomorphic maps between the intersection points. And this, in general, is some very difficult geometric problem to count these holomorphic maps. But the premise of our work and what allows you to actually explicitly compute anything is that you can exchange this for an algebraic problem by writing down resolutions of these branes in terms of specific building block branes. And so what this looks like is we have these specific branes that we call thimbles. And so these are these straight line branes. And so they sort of generate the category in the sense that I can build these more complicated figure 8 branes as chain complexes built out of these straight line thimbles. And so here I can see that, so the way we want to build these is literally like geometrically. So you can imagine gluing these straight line thimbles along the dashed lines. So the dashed lines are going to be the maps between the thimbles. So you can imagine that if I literally glue them back up together, we recover this figure 8 I've drawn. And then I can translate this geometric picture into a chain complex, where the things I call T1, T2, and T3 are these straight line thimbles, and then the maps between them are literally the maps of the chain complex. And then the thing I have in curly brackets is the equivariant degree, and there's a way to fix these. So once I have this resolution, I want to compute the HOM to get a knot invariance. This would just be the unknot because nothing's braided. And so I can see here I have 2 intersection points. So I would expect maybe there's a map, there's not in this case, so I just expect 2 intersection points, and that's what I get. And the reason I get that is because this I brane is actually dual to the thimbles in the sense that the HOM from T2 to I2 is just Z, and then the HOM from any other T brane to I is trivial. And so that just lets us very easily calculate the HOM from E2 to I2. And so the premise of what we do in our calculations is we are able to sort of take these figure 8 branes, make a resolution based on geometry, and then just compute the HOM with the I branes, and that will give us knot homology. And so it turns out in the one-dimensional case, this is very easy. But in more complicated cases, we won't want to take the product of multiple branes, and then we'll have to deform the differential in some way. But this differential, we're able to make an ansatz for it and completely solve everything using our code. So I guess I can stop here.
Thank you very much. Question from Greg upstairs.
Yeah, you were talking about thimbles. I assume these are Lefschetz thimbles for some superpotential. Could you explain that a little bit?
Yeah, they're, I guess, they are Lifshitz thimbles for the potential that I mentioned a couple slides ago.
I missed it. What was that potential?
Oh, I didn't actually give the potential. I don't know if I can
That's why I missed it.
go backwards. Yeah, I just sort of said, oh, here it is, yeah. I just mentioned that there is a potential. I didn't give its explicit form, but it basically has monodromy singularities at these marked points and also at the diagonal.
So is it something like a sum of logs?
Yeah, it's a bunch of log terms.
Of points?
Yeah, yeah.
Like what appeared in Gaiato and Witten's paper discussion of knot invariance, where they had a Landau-Ginzburg model where the superpotential was a sum of log zi minus zj times.
Yeah, it looks like this.
Okay.
My question is it correct to think of the links between 2 punctures as a tangent component of the Chern-Simons oscillation?
Sorry, could you say that louder?
Is it correct to think of the link between 2 punctures as the tangent component of the Chern-Simons oscillations?
I'm not sure.
Talking about the sigma, when I say tangent component, I'm talking about the coordinates in the string itself, in the worksheet coordinates.
Yeah, well, you want to think of these, they're coming from D-branes, not from strings. The strings would contribute to like the intersection points between the branes. Is that what you're asking?
Maybe you can ask it again during the coffee break. I think we need to move on. So thank you very much again.
Thank you.
So the last speaker for this session is Daniel Baldwin from King's on ICTP. It's about Coulomb and Higgs phases of G2 manifolds.
Okay, so thank you to all the organisers and for the opportunity to speak. So I'm Daniel, based here at ICTP, and I'd like to talk about Coulomb and Higgs phases of G2 manifolds. So to start, I have a slide just going over the background of what is M-theory and why do we care about G2 manifolds. So M-theory is a candidate for a theory of quantum gravity, and all the 10D string theories arise as various limits of M-theory. We know that at low energies it's described by 11-dimensional supergravity. And since it lives in 11 dimensions, to get 4D physics, we have to compactify the theory onto some 7-dimensional compact manifold, which I'll call X7. And then if X7 has a Ricci-flat metric, this space-time automatically solves the 11D vacuum Einstein equations. And then we get some 4D physics from Kaluza-Klein analysis of 11-dimensional supergravity. So what kind of manifolds can X7 be? Well, if we ask that we preserve n=1 supersymmetry in 4 dimensions, this forces the holonomy group of our 7D manifold, of the metric on our 7D manifold, to be the exceptional Lie group G2 by some general classification. And such manifolds are called G2 manifolds, and a nice thing about them is they're Ricci-flat. So they're analogous to Calabi-Yaos in string compactifications, but it's much harder to produce examples of them. Okay, so with the background done, now I want to speak about some work done regarding the physical interpretation of some particular kinds of G2 orbifolds that can be desingularized by a theorem of two mathematicians, Joyce and Karagiannis. And we'll see that different topologically distinct desingularizations of the same G2 orbifold that arise from their construction will correspond to Coulomb and Higgs branches of the moduli space of the arising 4D supersymmetric gauge theory. And then we'll see that by studying the moduli space of these gauge theories in more detail from differing viewpoints, we'll reveal an isomorphism between two a priori unrelated moduli spaces. And all of this is joint work with Bobby Acharya. So now we actually need to say something about ADE singularities and why they're important. So if we do the Kaluza-Klein reduction of 11-dimensional supergravity onto a smooth G2 manifold, we don't get anything very interesting. So we only have abelian gauge symmetry, and there's no possibility of having chiral fermions, which is bad because we need these for the standard model. And the solution is to let our G2 space develop singularities. So it turns out that non-abelian gauge symmetry in 4 dimensions comes from codimension 4 ADE singularities in our G2 orbifold, and chiral fermions come from codimension 7 conical singularities. But I'll focus just on ADE. So an ADE singularity is of the form C2 quotiented by a finite subgroup of SU2. If we take M theory on an ADE singularity, in the 7D spacetime, the low energy physics is described by 7D super Yang-Mills with gauge group GADE, where GADE is the group corresponding to the ADE singularity by the McKay correspondence. And inside of a G2 orbifold, ADE singularities occur along 3-dimensional submanifolds, which I'll call Q. And if we take M theory on some local model of the form Q times an ADE singularity, we'll get some 4D supersymmetric gauge theory arising from the reduction of the 7D super Yang-Mills onto this 3-manifold Q. But more generally, we'll be interested in G2 orbifolds with singular sets of the form Q times an ADE singularity, all quotiented by some finite group, which is freely acting on this Q, so we don't get any extra singularities. And it's known that the vacuum moduli space of the gauge theory arising from M theory compactification is given by the moduli space of flat complexified ADE connections on the 3-manifold Q mod K. And this space will generally be disconnected with many components. Previous work looked at just the identity connected component, but we'll provide an interpretation for the other various components. So Joyce and Karagiannis showed that if you have a G2 orbifold with a singular set of the form Q times an A1 singularity quotiented by Z2, so this is a special case of the above, then you can desingularize this to give a smooth G2 manifold if on the 3-manifold Q mod Z2 there exists a harmonic and nowhere vanishing 1 form. So you remove the singular set and glue in some family of Iguchi-Hansen spaces. And this all still works if this 1 form is replaced by a 1 form defined up to a sign locally on the 3-manifold, as long as it's harmonic and nowhere vanishing. So we'll call this a Z2 twisted one form. And this is the root of these topologically distinct desingularizations, which I mentioned. When studying the physics, it will be natural for us to generalize to consider more diverse ADE singularities and also higher order twists than what Joyce and Karagiannis considered. And so the goal now is to physically interpret these orbifolds and their various desingularizations. So as a simple example to illustrate all the results, we'll take our three-manifold Q to just be the 3 torus, times it by an AN-1 singularity and quotient by a freely acting Z2. Then we can see that on the 3-manifold, T3 mod Z2, we have a harmonic one form and 2 Z2 twisted harmonic one forms. And they're all nowhere vanishing because they're constant in this example. And so we're in the realm of this Joyce-Karagiannis theorem. And so following them, we should replace our singular set by T3 times n-centered Gibbons-Hawking space, which is the desingularization of an AN-1 singularity, with its hypercalometric, quotiented by some Z2. But the Z2 action on the Gibbons-Hawking space isn't uniquely determined, and there could be many different choices. And these will lead to topologically distinct desingularizations, and therefore the physics we get in 4D will be different because we'll have different Betti numbers. So for example, if we take n equals 2, we have 2 different desingularizations, x tilde c and x tilde h, and therefore we expect 2 different branches of our 4D gauge theory moduli space. But we can actually study this moduli space explicitly from 2 different viewpoints. The first way is by studying the moduli space of Ricci-flat special holonomy metrics on our spaces. And for the case of A-type singularities, this turns out to be the same as the space of Z2 invariant configurations of n points in R3. So this is a simple space to consider. So if we take n to be 2 and choose our Z2 to act in the following way, we see there's 2 possible configurations of 2 points. So the first one we'll call the Higgs branch. It has 2 parameters. The points are swapped into each other by the Z2. And then we have another branch, which we'll call the Coulomb branch, and it has a single parameter. On the other hand, it's known that the moduli space of M theory on this kind of orbifold is the space of flat complexified SU2 connections on the 3-manifold. And so we can also calculate this space, and we see again that there are 2 possible solutions. The first one, again, we'll call the Coulomb branch. It's identity connected and has a single parameter. And the second one we'll call the Higgs branch, and it's non-identity connected with 2 parameters. And we also learned something about the 4D gauge group by taking the commutant of these flat connections in SU2. So to summarize, we took M theory on this orbifold. We expected 2 different branches because there were 2 different topological desingularizations. We then studied the moduli space from 2 different viewpoints and saw that indeed there were 2 different branches, one of them 2-dimensional, one of them 1-dimensional. And then we can also do Kaluza-Klein analysis to determine the 4D gauge theories on each branch. So on the Coulomb branch, we have n equals 2 SU2 CP Yang-Mills at the origin, which breaks to U1 away from the origin. And on the Higgs branch, we have n equals 2 SO2 CP Yang-Mills coupled to 2 hypers, and this is completely broken away from the origin. And also, if I can just quickly say, we can also extend all of the previous to all A-type and D-type singularities and deal with higher order twists. And in fact, for the A and D-type cases, we can completely determine the moduli space of flat connections on any flat compact 3-manifold just from considering the moduli space of Ricci-flat metrics. And so in our second paper, we show this explicitly. So yeah, I'll leave that there. So thank you for your attention.
Thanks. I'm a bit puzzled. What does this have to do with G2? I think your holonomy is all sat inside SU3.
Yeah, so this example was quite special. So yeah, it was in SU3. That's why we got n equals 2 supersymmetry in our theories. But generally, these we'll expect these orbifolds to be describing the singular sets of some genuinely G2. Yeah, I mean, if I was quotienting by Z2 times Z2 on the bottom, then I would have been in G2, but not in SU3, and I would have had n equals 1. Yeah. We've studied those. So in that case, we'd have 3 1-dimensional Higgs branches.
Okay, one question here.
So in the Coulomb branch, you see it's SU2 supermuse. So you mean you also specify the global form of the gauge group, or it's just the SU2 Lie algebra for the theory?
Yeah,
do you mean it's SU2 or it's SO3 or?
Yeah, the global form I'm not I'm not sure. I guess we're just saying
Okay, so it's just
something
the,
about
the local information of the theory. It's just that tells you it's SU2, right? Okay.
Yeah, I believe so. Yeah.
Thanks.
Okay.
One more question here.
It also seems to me that all this analysis was pretty local. I mean, you always take a look. Is it possible actually in this Kovanov construction to take a further orbifold that you get chiral matter?
I'm not familiar with this.
I mean, this is this twisted connected sum where you have two Calabi.
Oh, okay. So we didn't.
Because I don't understand how you embed that in a global G2
Yeah,
manifold.
we didn't consider the twisted connected sums, but like there's some. I mean, the examples from.
He made Kovalev construction.
Yeah, but like the examples of, like the first examples of Joyce, like these torus quotients, they all have singular sets with various components, and they're all of the form that we considered here. So we can just take each singular set gives us a factor of our gauge group, and then we get the matter representations by seeing how the adjoint decomposes into this group.
Any urgent last question? Otherwise, let's thank Daniel and all the speakers collectively for very nice presentations. So we break for coffee and we're back here, I think, at 4:20. Or 4:30, so we have 10 extra minutes. 4:30.
So you did send it, you did upload it.
I just sent it. Hi, how are you?
The result applied to, he just showed the simplest example.
I wish he had done an honest G2, given that he was.
It's actually quite complicated.
Oh, I see.
So do you mind if I check and I get back to you?
It also works with compact. Compact
Especially if you can get some insight.
Cioè, dopo, grazie. Agnese?
else I could just forget.
And you can put in your pocket.
Yeah.
Whatever you want.
Okay. Yeah, maybe it might help.
This is
Yes.
forward and backward. Don't keep this pressed, because otherwise it goes off on the full screen. And if you keep press this one, you have the pointer. And you can do whatever you want.
Oh yeah, so the pointer.
You don't have to point.
Okay.
I mean, you can try, but there is an accelerometer.
Okay. Okay. If I point towards here, it will appear. Yeah.
Yes.
Okay. Let me try. Oui,
On commence à 30.
oui, j'ai vu.
Okay, so maybe we can resume. So the last from University of Georgia, and he will tell us about non-toric brainwebs, Calabi-Yau threefolds, and 5D SCFTs.
Okay, thank you very much for the introduction, and thank you very much to the organizer for the opportunity to speak. So the goal of today is to describe some physics, interpretation, and application of a series of recent mathematical works around mirror symmetry for so-called log Calabi-Yau surfaces, which include works of Gross Akin-Kill, Engel-Friedman, Akin-Kill, and most recently a joint work with Valery Alexeev and Ilya Argus that Argus talked about yesterday. So all of these works are in algebraic geometry. They're algebraic geometry papers with algebraic geometry motivations. And the goal of this talk is to translate and explain the relevance of these works to some physics question. And what I will talk about the physics aspects is some joint work with Ilya Argus, which is in preparation. Okay, so the physics context is the physics of a five-dimensional superconformal field series. So among the many remarkable predictions of string and M series, the existence of interacting five-dimensional quantum field series, and in particular five-dimensional n=1 superconformal field series. Okay, the fact that such a thing should exist goes back to Seiberg in '96, and then there's a very vast amount of literature studying these series. And there are essentially two main constructions, two ways to obtain this series starting from string or M series. The first one used singular geometry. You can start with M series in 11 dimensions and compactify it on a canonical threefold singularity X bar. So here, for all this talk, X bar, you should think about it as being a non-compact Calabi-Yau threefold, which is some local piece near a singularity. And so these singularities, these canonical threefold singularities, they are like three-dimensional version of ADE singularities for surfaces. They are singularities which appear at finite distance in the Keller moduli space of Calabi-Yau threefold. Concretely, you should think about it, you obtain them by taking a bunch of 2 cycles and 4 cycles in a smooth Calabi-Yau threefold, and the volume of this cycle goes to 0. And when you do that, the M2 and M5 branes around these cycles become light, and the theory describing this light object is expected to define a five-dimensional SCFT. So it's one construction where this theory is localized from a singularity in the geometry. Another way to produce some localized theory is to look at intersection of branes. And you can consider intersecting brane in type 2B string theory in flat space. So I will describe more precisely the relevant configuration of branes. But you consider branes which have a common five-dimensional intersection where the five-dimensional SCFT will live. And there are various possible brane you can consider. You can include 5 branes, 7 branes, or Yanti-folds, S-folds. And the general question for this talk, which is a very old question, is essentially the relation between these two constructions. And so first of all, let me say it's very much expected the M series construction, the geometry construction should be the most general. And so the most precise question we'll try to address is starting from a system of intersecting branes in type 2B string theory, which define a five-dimensional SCFT. Can we realize the same 5D SCFT as M series on a canonical threefold singularity X bar? And conversely, can we give an algebra geometric description of the class of singularities which appear that way? And there are cases which are well known. So if in type 2B you start with configuration of only 5 branes, then it's a very classical story that I will review in one moment. The M3 dual involves a toric Calabi-Yau threefold X bar. And I guess most generally some kind of expectation that the relevant geometry should be some non-toric geometry, but it will be part of this talk to try to describe precisely algebra geometrically what this non-toric geometry is. So what this thing is known in special cases for particular configuration of 5 branes and 7 branes. You get cones over del pezzo surfaces, possibly non-toric. And here I just listed 2 recent work by Bourget, Colinucci, Schaffer-Damecki, and Arias Tamago, Franco Rodriguez Gomez, which are maybe the most recent papers which try to address this question. And at the very end, I will comment on the relation of our work with their work. Essentially, our work can be viewed as a generalization of their work. Okay, so I will start here by an overview of the results before going into the details of the arguments. So the first main result is that if you start from a consistent configuration of 5 branes and 7 branes, then there will be an algebra geometric construction of a canonical threefold singularity X bar, non-toric in general, which will be the dual, the M3 dual of the configuration of branes. And here the key point which will need to be addressed is what do we mean by consistent? So maybe a better word for consistent should be maybe supersymmetric. So really a configuration of branes which define your a well-defined 5D SCFT. And we'll give some kind of algebra geometric characterization of consistency. And here the result in the other direction. So the claim will be that the canonical threefold singularity X bar which appear here has a very special shape. And conversely, all the one of this shape will come from this construction. Okay, so here is in words what this canonical threefold singularity which appear looks like. So the claim is that there will be a type 2B dual brane description if and only if your X bar, which is three-dimensional, complex dimension 3, is actually a fibration in surfaces over a base that I know by delta, which is just a disk containing 0 in the complex plane. And the general fiber of this family is smooth. And the special fiber of the 0 is a very explicit singularity, which has some name in algebraic geometry. I will come back to them later, as a simple elliptic or cusp or degenerate cusp singularity. So here is a picture to have in mind. Our X bar, the canonical threefold singularity which will appear, is not honestly three-dimensional. It's really a one-parameter family of surfaces. And the general surface is smooth, and only the one of the 0 is singular. So you can think about this geometry as a total space of a one-parameter smoothing of a surface singularity. And so this singularity which appear, this surface singularity which appear on the special fiber, simple elliptic cusp degenerate, they are well known in the algebraic geometry literature. They are examples of semi-log canonical singularities, which were introduced by Kohler, Scheper-Brandt in the 80s. And actually, in the previous result, I should have been more careful. This result describes dual of configuration of branes, which include 5 branes and 7 branes, not more general type of branes. But one expects that if you also include extra objects like orientifolds or S-folds, there will be a similar description in terms of smoothing of more complicated semi-log canonical singularities. But I will not do that in this talk because actually the algebra geometric part of this story is not fully understood. Okay, so the plan of this talk, I will first review rather quickly the known story of webs of 5 branes, how they are related to toric, Calabi-Yau threefold. Then I will talk about webs of 5 branes with 7 branes, which is the main topic of this talk, and how we can think about them algebra geometrically in the language of polarized log Calabi-Yau surfaces. And then how to produce a M3 dual Calabi-Yau threefold from mirror symmetry, but a non-toric version of a mirror symmetry. And physically, the non-toric nature of the mirror symmetry will be related to the existence of Wash-it instanton from the A model point of view on mirror symmetry. And at the very end of the talk, I will comment on the fact that these Wash-it instantons have a dual, very different interpretation as 4D n equal to BPS states of very particular series, which might also be of independent interest. Okay, so I'll start at the very beginning. So in type 2B string theory, we have PQ5 branes for every PQ coprime integers, which are related by S-duality. And one way to cook up a web of 5 branes, so you pick finitely many PIQI, such that sum of PIQI is 0. And then you consider type 2B string theory on essentially flat 10-dimensional space, where all the branes have a common 5-dimensional space. And the remaining one-dimensional parts of the brane live inside a copy of R2. Oops. A copy of R2 inside the space-time. And they look like as on this picture. So in some appropriate coordinate, you can show that to get supersymmetric configuration, the PQ brane, its one-dimensional part inside this R2, should be a line of slope PQ. Okay, so here in this picture, I just have a bunch of half lines going through the origin. There are various PQ5 branes, and they all intersect at the origin. So this origin in the full space-time is a 5-dimensional locus, where the 5D SCFT is living. And in this case, there is a well-known recipe to produce a Calabi-Yau threefold, where the M3 dual is living. Starting from this configuration of 5 branes, you can consider a dual polytope. Essentially, for every PQ, you consider the orthogonal primitive vector, and you add them up. You get this dual polytope picture, which is some lattice polytope. And then out of this lattice polytope, you can make a toric geometry construction. You can consider the cone over this polytope. It will be a three-dimensional cone. And you think about this cone as a fan of an affine three-dimensional toric variety X bar. And this X bar will be the geometry we are looking for. It will be some affine singular geometry. And because of this cone structure of the fan, actually this X bar has the same kind of structure as advertised at the beginning. Is that the natural map to C. It's really a family of surfaces in a natural way, where the general fiber is a copy of C star squared, and the special fiber is one of these singular surfaces. Okay, so these singular geometry are a bit difficult to think about. There is something better you can do, better to visualize, like essentially resolution of these singularities. So physically, it means going to the Coulomb branch of the 5D theory. On the brane point of view, it means perturbing the configuration of 5 branes in a kind of generic way so that they don't all go to the origin, but you perturb them. And then you connect them in between in some kind of balanced graph, which is this blue picture on the screen. And if you do a generic perturbation, you get a trivalent graph, which is dual to a triangulation of your polytope. And such data, if now you do this toric construction for this triangulated polytope, you take the cone over that, over the triangulation, view that as a fan, and take the corresponding toric variety, you produce a toric variety X, which is smooth, and which is a Crépinch resolution of the singular toric variety X bar. And the thing which is important in this toric dictionary is that if you think about what is the central fiber of this X, what X0 looks like, it looks like the web. So the faces of the webs and one-dimensional correspondence with the irreducible components of X0. So maybe here is a better picture. So here in the toric situation, everything is toric. X bar is an affine toric threefold, which has this map to a one-parameter base. The geometric fiber is C star squared. So this thing is just C star squared. In the middle, you get something where the singularity is. And X is a Crépinch resolution. So it's the same thing as X bar away from 0. And over 0, it's a bunch of surfaces which, when you go to the singularity, gets contracted. And the picture of these surfaces is controlled by the picture of the web. Okay, so here I just stated the duality. If you start with this web of 5 branes, it's one way to get this 5D SCFT, and I produce a recipe to produce a Calabi threefold. And the claim is that you get that with the M3 dual. And if you ask why is it true, so can you derive it in a physics way, and there is a well-known derivation. And one way to do it is to, rather than to start with your 5D theory, you compactify it on a circle. You get a 4D n equal 2 theory, and by standard series of string dualities, it's the same thing as type 2B string theory on a non-compact Calabi threefold Z defined by this equation UV equal F, where F is a Laurent polynomial with Newton polytope P. So you should think about the curve F equal to 0 as being a curve in C star squared. The Seiberg-Wheaton curve of the 4D n equal 2 theory. And the way it's connected to the brainweb is that this curve in some appropriate tropical limit looks like the brainweb. So essentially you get this curve by adding a small circle over the edges of the graph to produce a Riemann surface. And something which will be very important later for the non-toric generalization is that this curve in C star squared has a natural compactification inside the toric variety YD. And these compact toric varieties, this curve live inside the linear system of the ample line bundle L, which is defined by the polytope P. So if you have a polytope P, you can view it as a momentum polytope of a polarized toric variety YDL. So this picture naturally compactify, and the equation of this curve is a section of this line bundle L. Okay, so this thing was a review of the non-toric story. Now we'll start introducing 7 branes, which will put us outside of the toric world. And here we'll start making some comment about 7 branes without 5 branes. We'll add 5 branes and 7 branes together in 1 minute. So you again start with type 2B string theory on this. Maybe you might think of starting with flat space with this particular R2 factor where the previous brane picture was living. And or you can add to this picture a PQ7 branes, which fill all space-time, except they are localized at some point inside this R2. And because we want to have 7 branes which ultimately can be put on top of each other to produce a conformal field theory, I will think of about picture like that. So what is this picture? It starts by being this R2. And then, so previously on this R2 I had natural coordinates where the 5 branes were straight lines. And now when I introduce a 7 branes introduce some singularity in these coordinates. If you go around such a 7 branes, there will be some monodromy for these coordinates. And so the red line here is supposed to be some kind of monodromy cut, so that when you go across this line, you apply this monodromy transformation. So on this picture, the red cross are the 7 branes. And actually, this monodromy is unipotent. It's like 1, 1, 0, 1. So there's a particular direction, which is a monodromy invariant direction. And something I will do, which will essentially not change the physics, I can always move these red points along the monodromy invariant direction. So in this picture, I take all the monodromy invariant direction going through the middle point here, because ultimately I want to push all the 7 branes on top of each other. Okay, so we look at such a picture. But physically, this picture will be equivalent if we do so-called Anani-Witten move. You could just push one of these singularity along a monodromy invariant direction, and then draw the cut in the other way. And you will get a different picture which describes the same physics, and they should be considered as equivalent configuration of 7 branes. And you might ask about classifying all these 7 branes up to this move. And our first claim, which is some kind of algebro-geometric answer for this problem. So the first claim is that these configurations of 7 branes coming together up to these natural moves are in one-to-one correspondence with some non-compact algebraic surfaces I will describe in 1 minute that are defined by U and that I call interior of log Calabi-Yau surfaces. So topologically, this geometry is well known. If you think of 7 branes in the F-theory context, U is just a topologically torus fibration over the previous picture, where over the 7 branes you have a singular torus fiber, where the particular cycle shrinking depends on what is PQ for the 7 branes. So this picture is well known as being a geometry which can be attached to a configuration of 7 branes. What is maybe not fully known is the fact that this geometry as a complex algebraic variety can be described as the interior of a log Calabi-Yau surface. So you can write this geometry U as a y minus d, where y is a smooth projective surface, and d is a singular normal crossing anti-canonical divisor. And I will explain in 1 minute how do you produce this data of y and d. So maybe just to orient ourselves, if we start with something, if there is no 7 branes at all, this geometry is just c star squared, and the compactification is like a toric compactification of c star squared. In general, this geometry, algebro-geometric, is a generalization of c star squared. It's an example of a cluster variety. So it actually contains many copies of c star squared. Actually, for each presentation like that, where you push 7 branes for infinity, there will be a copy of c star squared inside. And when you do such a move of pushing one singularity from one side to the other, it's like going to a different cluster chart c star squared on this geometry. Okay, so here the first thing we learn is that you should think of configuration of 7 branes are being attached to these non-compact algebraic surfaces U, which are like non-toric, if you're non-toric generalization of c star squared. And now we are adding 5 branes to the picture. So now we combine the 2 stories. You can start with a web of 5 branes as before, and you can try to make some 5 branes end on some 7 branes. And so the fact that it should be interesting was suggesting a long time ago, for example, by De Wolfe, Anani, Iqbal, and Katz in 1999. And there is some even more interesting theory where you allow several 7 branes. Sorry, here there is a typo. I mean several 5 branes ending on the same 7 branes, which was suggested by Benelli, Benvenuti, and Tachikawa. And then you get this kind of picture. So here, the picture on blue, there is a web of 5 branes as before. But now, some of these 5 branes are ending on these red crosses, which are 7 branes. And the condition for supersymmetry, so the PQ direction of the 5 brane should be the same thing as the PQ direction of the 7 branes. So you can get this kind of picture. So in this picture, you only have each time a single 5' ending on the 7 branes. In the picture on the right, here I have a multiplicity 2, which means actually there is 2 parallel 5' on top of each other, which end on the same 7 branes. Yeah, that's why. So I mentioned it. Yes, there is definitely a misprint. I mean, several 5' ending on the same 7 branes. Yeah. And so in particular, when you do that, in particular, the web you start with does not have to be generic. Okay, in my previous picture, I was doing generic web, so the picture was trivalent. But here on the left, on the right-hand side of the screen, here I have a 4-valent vertex. So I can start with a non-generic web where I have several 5' on top of each other, and ask all of them to end on the same 7 brane. And so here there is some kind of basic issue, which is known since the beginning of this subject, which is maybe not all choice of such pictures are consistent or supersymmetric. So there are things called S rule or R rule or various type of consistency conditions. So the basic thing which can happen that I will not describe in details is that when you move one of these red cross across a picture, then there is this Anani-Wheaton transition where the number of 5 branes ending on 7 branes can change in some well-specified way. And sometimes if you start with a random picture and you try to do that, the number of 5 branes ending on the 7 branes become negative, which is some kind of violations of supersymmetry. So you cannot start with arbitrary pictures with some kind of restrictions. And in the literature, you can find various proposals for what the correct set of restrictions should be, but maybe not something which looks like fully 100% one-to-one working proposal. And here we'll give some kind of algebro-geometric reformulation, and we'll see from this algebro-geometric reformulation why it is actually a very subtle problem. So algebro-geometrically, we start with, okay, let's start with such picture. So we just first start with a blue picture. It's a web of 5 branes as before. And so we know that attached to this picture, you can draw a polytope. And this polytope defines your toric surfaces, y bar, d bar, and a line bundle L bar. And now, using the 7 branes, we'll modify this geometry. So here is this polytope. You already think of this polytope as being a picture of this toric surface, y bar, d bar. So this toric surface is a place where the mirror curve live in the C star squared of this toric surface. So how do I modify this geometry to include the 7 branes? The 7 branes correspond to some unbounded edges of my web. And these unbounded edges correspond to rays in the fan, which correspond to boundary divisors of the toric variety. And so what I will do is each time I have a 7 brane, I will look at the corresponding boundary divisor on my toric variety. For example, if I take the 7 brane here, the corresponding boundary side of my toric variety will be here. And what I will do, I'll take a point on this boundary component, and I will blow up this point up. I blow up this point. So this thing is a non-toric operation because I blow up something which is not a torus fixed point, but a point on the boundary. So here in this example, I had 6 7 branes I was adding. So I will blow up 6 points, and what is in red on the picture are the exceptional curves I produce when I do these blobs. Okay, so when I do this non-toric blob, I get the new surface y, and what I denote by d is a strict transform of the toric boundary d bar. And then the interior u I was talking about is really y minus d. So the non-toric geometry u, which is determined by the 7 branes, is like if you remove the boundary of this picture, you will get some non-compact algebraic surface, which is a cluster variety I was talking about before. Okay, so this thing until now only see the web of 5 branes and the set of 7 branes, but how do they interact together? This thing will affect the choice of the line bundle, ample line bundle on this non-toric geometry. So if I have some 7 branes like here, it corresponds to a blow-up in the geometry, which corresponds to some exceptional curve EI. And on these 7 branes, I have some number of 5 branes ending, and I call this integer AI. And I use this data to cook up on this non-toric geometry some ample line bundle, L, which is a pullback of the line bundle L bar, which comes from the toric story, involving only 5 branes. And then I subtract to it sum over I, AI, EI, where the EI as an exceptional divisor. So maybe this notation is more a divisor notation. The divisor corresponding to the line bundle L is the one from L bar minus sum of the I, AI, EI. So concretely, as we'll discuss in one moment, if you have a curve which is defined by a section of these line bundles, then this curve will intersect the exceptional divisor EI in AI points. Okay, so here essentially what I explain here is an algebraic geometric recipe. We start with a picture. You produce a surface and a line bundle on it. And now the claim will be that what you started with is consistent, is a kind of supersymmetric configuration, is a line bundle you constructed is satisfies some natural positivity condition. Let's say if it's an F line bundle, if it has a non-negative intersection with every compact curve in your geometry. And actually, there is a few special cases I will, extra condition I will skip for now. Let's just remember that the kind of algebraic geometric condition which will determine if the starting picture is consistent or not is a positivity condition. Is this line bundle F or not? And here you see why this condition is actually extremely subtle, and in my mind, it's kind of explained why in the physics literature it looks like a difficult question. Is that this surface Y we construct this, you start with something toric and you blob many, many points. Actually, the cone of algebraic curves inside such surface does not have to be finitely generated. It might be finitely generated in special cases, but in general, it's not. So actually, to check this Neffness condition, you need to check, it's not obviously reducible to checking intersection with finitely many curves. It's a kind of non-trivial algebraic geometric condition, which has no obvious combinatorial interpretation. And here there is some lemma which connects this condition, which may be the most obvious picture, which is that, so if this brane is consistent in this sense, then there will be a smooth curve, C, inside this non-toric geometry defined by a section of this line bundle, which will really be the same, the analog of the mirror curve in the toric situation. So here is a picture of what the curve looks like in blue. So it's really a curve which, in some appropriate tropical limit, should look like this brane ending on some 7 branes. Okay, so in the toric situation, it was just a curve in C star squared. But now it's no longer a curve in C star squared. It's a curve inside a non-compact holomorphic symplectic surface, some cluster type varieties. And the physics interpretation of this curve is exactly the same as in the toric situation. So if you compactify your 5D theory on a circle, you get a 4D n equal 2 theory. And the claim is saying the same thing as type 2B on the Calabi-Yau threefold Z, defined by UV equal F. But now the difference is that F is a defining equation of this curve inside this non-compact U. So the curve is no longer in C star squared, but inside this a cluster generalization of C star squared U. And as in the toric situation, if you go through a usual sequence of string dualities, you would expect that the M-theory dual that you are looking for, so the canonical threefold singularity such that M3 on it engineers the same 5D SCFT as a web of 5 branes with 7 branes, should just be the mirror of this non-compact Calabi-Yau threefold Z. But now the main issue is that this Z, we're no longer inside standard toric mirror symmetry. So the mirror will not be toric, and it's apparently not completely obvious starting from this Z. How do you produce the mirror? And so I will say a few words about how to do that. So this thing will be some kind of reformulation of what Julia described yesterday in her talk in a more algebraic or geometric way. So first we'll do something which actually is well known in some special cases. So the way our story starts is as a web of 5 branes and 7 branes where 5 branes end. So if you want the 7 branes are near to infinity, but then you can try to move the 7 branes inside and see what happens. And here some statement is that if what you start with is consistent in the algebraic geometric sense I've defined, then there is no obstruction to push in the 7 branes along the monodromy invariant direction until they are no longer attached to any 5 branes. So what do I mean by that? You could try to push 7 branes, for example, a C1 here. I push it, I push it, I push it, and at some point I hit a vertex of the web, And here there is some Anani-Witten transition happening. If I try to do it further, the local picture will change, of the web will change. In particular, the number of brains attached to the 7 brains will change. And what the lemma is saying is that you can do it such that this number decrease, and maybe you continue, it will decrease again, until at the end, the 7 brains is attached to nothing. So here is a well-known case. If I consider this a picture which is related to a local del pezzo, you can just push the singularity inside, and here it's easy. Just as the first time the singularity cross is no longer get attached to anything, and so you get this picture on the right. And the reason why on the right the blue picture looks like some curvy thing is because on the left it looks like some broken piecewise linear thing, but once I've pushed the singularity inside, this blue thing, while crossing the monodromy cut, are actually going straight. So even if they look bent, actually they are straight because of the monodromy. So actually the thing is actually a single straight line. There is no corner in the blue picture here. And okay, so this example is, as I kind of well known because it's related to like cone over non-toric del pezzo surfaces. So the claim is that it's possible in general for any consistent configuration of 5 brains with 7 brains, which is consistent in the way I've defined. So here is some more complicated picture. You push these singularities inside, and then you get this kind of picture. One of the 7 brains live inside and are no longer attached to anything. And maybe I should have mentioned the fact that this thing is possible. Somehow our definition of consistency used some algebraic geometry, and the proof of that is some kind of algebro-geometric argument. So there will be, in some way I will not take the time to explain, there is somewhere some, you want to produce a minimal model of some geometry, you need to do a sequence of flops. And this move, so the fact that this flop exists is consequence from general birational geometry. And it translates into the fact that in the picture it's always possible to do that if you start with something which is consistent. And now we'll just use this picture to produce the mirror. So recall that the mirror is supposed to be a family of surfaces over one-dimensional base. And what we'll do first is to produce a central fiber X0. And to do that, we can take inspiration from the toric situation. So in the toric situation, the brain is, the web is essentially a picture of this central fiber. The various faces of the brain are the various irreducible component of this central fiber. And here we want to do the same. You want to think about this picture, this final picture where the 7 brains are inside. We want to think about them as being a picture of a normal crossing surface where the various faces are various irreducible surfaces glued together according to the picture. And how to do that? So first you can start with the blue picture. So forget the 7 brains. Just start with the blue picture. And starting from the blue picture, we know how to produce a toric dual. Okay, so we know how to produce a toric dual that I denote by XW, which is a toric Calabi-Yau threefold. And I denote by XW if you start with the web W, and which is possibly singular because this blue web you start with is possibly singular. It's possibly non-generic, like there is 4 valent vertices here, for example. So the corresponding dual toric geometry will be singular. And then the geometry we care about, the non-toric geometry, will be obtained as a non-toric smoothing of this toric geometry. So the statement is that if you know how to push these 7 brains so that at the end they are no longer attached to any 5 brains, then there will be a recipe on the algebro-geometric side starting from the toric X0, XW0, how to deform it to make it non-toric and to make it dual to this picture. So roughly, the operation of pushing 7 brains and getting some blue side smooth is really, in the geometry, means take one of these toric surface. For example, here there is this face of the blue web, which starts its life as being a toric surface. And then pushing these 2 singularities inside means this toric surface with this toric boundary deform into a non-toric surface with a non-toric boundary. And the fact it's possible follow from some deformation theory, actually quotient singularities that I will not go into, but which can be argued. And it's not it's not something which is obvious. You need to be kind of lucky to see, okay, what kind of singularity here in your toric surface is a quotient singularity of a type which happens to admit a nice one-parameter smoothing, and you can use that to construct your non-toric geometry. Okay, so that way you construct this normal crossing surface x0, so maybe here's a better picture of what we are doing. Here, what I try to explain is starting from the picture with the 7 brain inside, you cook up this x0, this normal crossing surface. And once you have this x0, you will produce the geometry x, a threefold, by smoothing this surface in a one-parameter family to get a full threefold x. And again, by some deformation theory, you can argue such smoothing exists. And in addition, once you have this x, you can argue that all the compact surfaces inside x0, you can contract them to a point to get a geometry x bar, which will be the singular geometry with a canonical threefold singularity. Okay, so at the end of the day, starting from our consistent web of 5 branes and 7 branes, there is really an algebraic geometric recipe to construct this x bar, which is in general a non-toric canonical threefold singularity. And actually, along the way, we produce actually a cryptont resolution of it by this picture of moving 7 branes inside 5 branes. Okay, so this thing is a sketch of the main construction, starting from a consistent web of 5 branes with 7 branes, how to produce this geometry. And I claim that you can do the converse. So actually, it's a kind of almost one-to-one correspondence. If you start with such picture, then you can run a mirror symmetry backwards in a way that will not explain to produce a log-Calabi-Yau surface with a positive enough line bundle, which will correspond to a web of 5 branes with 7 branes. So actually, all the geometry which appears from the picture we started with, algebraic geometrically, you can just say, okay, they are all the canonical threefold singularity, which look like that. So they look like smoothing of a central fiber x0 bar, and if this x0 bar is in the small list I've given, simple elliptic, degenerate curves or curve singularity, then this thing will come from a type 2b brane description. It's a kind of algebraic geometric characterization of the geometry you get. So maybe what I just explained here might seem a little bit mysterious. In many places, I said use deformation theory to produce these non-toric geometries, but you might ask, can we be more explicit? How do you get this non-toric deformation? And in particular, from a physics point of view, what happens? And actually, physically, there is something which will produce for you the deformation. So here is a statement, which is that you can produce these non-toric geometry. Let's say you can produce the equations in some kind of algorithmic way from some algebraic gadget called a scattering diagram with initial rays coming out of the 7 branes. So scattering diagrams are objects which have been introduced in the mathematical mirror symmetry literature, starting with Consoy-Sommermann, Gross and Siebert, Gross I can kill, and so on. So they look like the picture on the bottom. So the picture we really live in the R2 where the web was drawn and the 7 branes were drawn. And there will be some rays coming out of the 7 branes. And these rays are decorated by generating series. And when 2 rays cross, then there will be an algorithm to produce new rays with new generating series attached to them. And the claim is that if you have such a picture, you can use it to cook up a geometry, which are the kind of non-toric geometry we are producing. And from a physics point of view, see what's going on is actually completely natural, is that if you do a mirror symmetry, you are essentially starting with an A model, and you try to construct the space, a mirror, this space of points on the B side. And on the A model side, you can have watch its instantons. And here is a picture on the base of these rays, which come together and produce new rays. The claim is that they are essentially a shadow of holomorphic curves, which lives inside this surface U. So there's essentially holomorphic disk in this non-compact geometry U with boundary on this torus fiber. And so if you are entirely in the toric situation, if there is no 7 branes, then there are no such a thing at all. So in the non-toric situation, you have 7 branes which produce singular fibers which makes the existence of this curve possible, because now you have cycle collapsing at these singularities, and so this holomorphic curve can close up to produce such a picture. And these holomorphic curves are exactly the kind of watch-it instance-on correction, if you think about the XYZ picture of mirror symmetry for this Lagrangian torus aberration. Okay, so algebra geometrically, there is by now a full theory of so-called punctured Gromov-Witten invariants developed by Abramovich and Gross and Zibert that we might use to make this picture precise. And I guess Mark Gross will talk tomorrow in his talk about these algebra geometric aspects of mirror symmetry. Okay, so what I claim is that starting from the picture of 7 branes, you can algorithmically produce a picture which looks like that. You have some explicit rays, and when they cross, you have more rays, and so on. It's an iterative process. And once you know this picture, there is some recipe to produce some mirror geometry. So here, let me make a comment. So there is a case which is easy, which is if all 5 branes ending on 7 branes are parallel. So for example, what happens here on the picture on the left, where I push the right thing, they are all parallel. Like it's all PQ, but all the PQ are all parallel to each other. So in this case, the corresponding piece of the scattering, the rays which are emitted, are all parallel, so they do not intersect, they do not talk to each other. So the picture is really easy. And we can show that if you run the algorithm starting from this scattering picture and work out what is a non-toric mirror, in this case, you can write down explicit equations, and you recover the explicit results of Bourget, Colinucci, and Schaffner-Nameki that they obtain in completely different methods. So essentially what they use is that if everything is along the same direction, you can make some kind of dimensional reduction or T-duality to go to a different frame, a different type 2A frame, and then they do some gauge theory argument for what the equation should be. And here we recover them as a special case of our general formalism. And here you see why things are complicated in general. So in general, if your 7 branes are not, if your 5 branes ending on 7 branes are not all parallel, then the rays emitted by the 7 branes will intersect, and then the scattering will be very complicated. You will produce more and more and more scattering, and writing, if you want explicitly, your non-toric mirror is in principle possible algorithmically, but very, very complicated. Okay, I will just end by some kind of aside, which is here, so essentially here the key physical input, the key difference with the non-toric situation and this toric situation are really these watch-it instantons. And the last comment is that these watch-it instanton, you can think about them in a dual way as BPS states in some n equal to a 4D system. And so what should not confuse is not related in any simple way to the 5D theory I've been talking about. It's not the 5D theory on a circle. It's something else. It's some auxiliary theory. And you get this auxiliary theory by taking just a D3 brane probing your configuration of 7 branes. And that way you get a 4D n equal to theory, which is a rank 1 theory. So its Coulomb branch is identified with the place where this picture is drawn. So essentially, you have some D3 brane, which is just a point in this picture. And the D3 brane can move around, and so you get a one-dimensional Coulomb branch. And equivalently, you can think to an M5 brane wrapping a torus in this torus aberration I was drawing. And now by a sequence of standard string theory dualities, you can see that the watch-it instantons I was talking about are really BPS states of this theory, because you can think about it as string junctions between the D3 branes and the 7 branes. Is one way to think about this graph in this picture. These are string junctions. Or equivalently, you can think about them in this picture as a projection of this kind of holomorphic curve, which are some kind of M2 branes. And in the M theorization, they will also define BPS states of this theory. And from this 4D n equal 2 theory point of view, the scattering diagram I've been describing is some kind of way to organize the Conservich-Saberman wall-crossing formula for BPS states in this 4D n equal 2 theory. So the fact that you have two rays colliding, which produce new rays, is a reflection of the fact that in some places, in the Coulomb branch of this 4D and equal 2 series, sometimes you have some BPS states and some, along some walls they disappear, some other might appear, and all that, which is described by the conservation wall crossing formula, is described by this picture. And so here you might believe that this picture indeed might be complicated because actually the BPS state of a random 4D and equal 2 series can be quite complicated. So the complication of this picture is as complicated as what you can find in this context. Okay, so essentially, so the conclusion was to go from this toric to a non-toric situation, where this Washington instanton. And if you want, you can think about them in this dual way as example of 4D n equal to BPS states. And I will stop there. Thank you for your attention.
Thanks for the beautiful talk. Any questions?
So this mirror curve, is this, in which way is it given? Can you sort of have a Bergman kernel on it, and so that you do a topological recursion on it?
Yeah, so it's something that, indeed, so you can think of this story as really some non-toric version of usual toric mirror symmetry, and so everything you might like or know in the toric situation, you might ask either a version for it in the non-toric situation. For example, can you do topological recursion? And I don't know the answer to that. So usually the general setup for topological recursion is like a curve in some holomorphic symplectic surface.
Right.
And I guess it's well known how to do it if your curve lives inside maybe the cotangent bundle to another curve, or in the toric situation if it lives inside C star squared. So here the question is how to do that if your curve lives inside some kind of cluster surface. What is the proper way to do that? And I don't know the answer to this question.
Okay.
But there should be one way to do that, which then should compute the topological string of this non-toric Calabi-Yau threefold we are producing.
Great, thank you.
Okay.
So the 5D superconformal field theory has an SU2 times U1 symmetry, SU2R symmetry, and U1 for the instanton current. And so I'm wondering if you turn on gauge fields for that, the non-dynamical gauge fields for that, is there a geometrical picture in terms of either M theory or in terms of our brains?
So,
in 2B?
Just to check, you said like non-dynamical, so do you still expect that
Take
to
the SU2R symmetry of the 5D
right,
super Young-Mills. Introduce a gauge connection for that.
Yeah, I don't know what his deformation correspond to. Even in the traditional toric situation, I don't know the answer to this question, but maybe we should talk more.
So in the standard picture of this M theory on toric geometry, you have the 5D at CFT, right? The BPS states can be encoded in the BPS quiver, which is the quiver you can read just from the toric diagram by the brain tiling, etc.
Yeah.
And also the word crossing is just the quiver mutation at that level. So do you have any thoughts or comments like based on your last point? Like what kind of BPS quiver should I think of from this generalized toric polygon or non-toric geometry?
So I mean, the only comment I can make is that there are several works in the physics literature which try to address this question, like to produce some kind of BPS quiver since it's a non-toric situation. And so the only thing I can say is that once you have a well-defined non-toric Calabi-Yau threefold geometry X, there's a well-defined mathematical question which is study the derived category of this X. Can you produce an exceptional collection? And can you get a quiver out of that? And so this thing is a natural question which has not been explored. So yeah, in the physics literature, there are various proposals for how to do that. I guess in some cases, how to produce some quivers. And now the kind of natural question is it really true that these quivers describe the derived category of these geometries? And yeah, it has not been explored.
I can ask a question in the same vein. Do you expect these 4D BPS states that you mentioned at the end were representing the Washington instantons to be a subset of the BPS spectrum in this 5-dimensional SCFT compactified on the circle?
No, so I think these two 4D theory are really, they are really distinct. So in the language of this non-compact holomorphic symplectic U, you get the 4D theory related to the 5D theory on a circle by, one way to say it, on the M5 brane inside this curve, inside this geometry U. So maybe you can just, so we have this geometry U, which is this torus vibration over some base, and inside that I have some curve C. And if you take a M5 brane on C, you get the theory which is related to the 5D theory on S1. But the worldsheet corrections are related to the 4D theory, which is obtained by putting an M5 brane on the torus in these vibrations, which in general are two different things. So there might be a very confusing case where C has genus 1, and then maybe by applique rotations it happens to be the same thing. So actually in the example I drew, it might be the case that this is one of these weird examples, but from a general viewpoint, there are like two different 4D n equal 2 theory which are not related in an obvious way.
Any other question? Okay, well, in that case, let's thank Pierrick for the very nice talk. That's it for today.
Thank you, Boris. Thank you very much for your.
Thank you for asking me.